It's going super slow. Come on. And it's showing me the 300 windows that I have open in preview.
So I'll give a voiceover as Juan goes through his screen share journey, as Mike alluded to in the chat. Welcome back to our session. We've just started the recording, so this will be the part that's posted up. But we're basically reconvening for our final session, which is about complex systems and statistical analyses. And we've got all our speakers lined up, and it'll just be a few more moments as we get all of our presentations ready for presentation. I'm sure we'll have a number of people also joining in the next couple of minutes as we go through our start time. So.
I cannot, for some reason, it's not letting me do what I need to do.
Juan, if you want, you can feel free to just send me your slides and I'm happy to share them. And you can just say next slide when you need it.
Yeah, well, oh, it is behaving. It's, you must have enabled it.
Juan, do you think it's an issue that will be solved here in the next few minutes, or would you like to sign off and take it offline?
Juan just disappeared.
He just disappeared. Okay. So I think that's might be our answer. So I think we will go ahead and start the session because Juan will be speaking about halfway through the session. So, oh, here he is. He's back. Juan, we're going to go ahead and start if you want to try to, yeah. Okay, so with that, we'll hand over our first talk to Dr. Ella Gale.
Hi, now I have the screen share.
Yep.
Let's see.
Mm-hmm.
Oh, it's all right, Windows is helping.
Mm-hmm.
Right, presumably you can all see an amazingly colored slide.
We can't see it and loving the color scheme.
Okay, thank you. Pleased to meet you all. I'm Ella Gale and thank you for inviting me to this. And it was a bit hard to know quite what to talk about. So I have decided to focus on some of the tools that I have used and how they can be applied to other problems. Because I see that this area is an area that requires a multidisciplinary approach, and that requires taking ideas from other fields. And the title of my talk is The Problem of Multidimensional Problems. So you guys are going to have multidimensional data. If you go into the lab and you run lots of experiments, you're gathering as much information as you can. I'm sure any information you get from space, and this is far outside what I know about, but I'm sure you have lots and lots of data in that area. And you have complex problems to solve. And I mean complex here as in difficult, as well as complex as in complexity. And you don't know exactly which data will contribute to the solution. Obviously, you have some ideas as because of the field you're in, you have your knowledge, but you don't entirely know. And this is the sort of problem that comes up all through science at the moment, especially in the general area that I'm in, which is machine learning. So I'm going to try and address some of that here. Okay, so what is multidimensional data? So if you have two-dimensional data, I'm sure you're all aware, you can plot that as points in a 2D space. The easiest way to think about multidimensional data is that this is now points in a multidimensional space. And all of the stuff in machine learning and sort of the breakthrough of computers recently is about dealing with this sort of data in this sort of space. And it's a good idea to have a concept of this being a physical space, I find. So what is multidimensional data like? People do say that humans can't visualize beyond 3 dimensions. I don't think that's quite true, in that I feel that if you study in this area, you can learn a little bit about what it's like. But it's basically like this. So if you can't see my slide exactly at home, that's like a star field. So I'm not necessarily saying that the universe is multidimensional. That's a question for physicists, and I'm not one of those. But when you think of data points in the space, think of them spread out like the stars are here, very far apart. And there's lots of space in between the points. That's the easiest concept to have in your mind here. So, okay, now the other thing I'll be talking about, what is machine learning? So machine learning takes a set of known input data. So we have our data we measure, however we get it, and then we learn a model from that, and we use that to generate answers for new data. So get a model of our system or to predict something new. So the big breakthrough recently in machine learning, I'm talking about the last 5-10 years, was suddenly there was a lot of data available on fast computers. And machine learning algorithms got a lot better because suddenly you could throw a lot more data at the problem. Now this only works if data is easily available or cheap to get. And having lots of data can lead to the risk of overtraining if you have to make a very large algorithm as well. And this costs time, money, and storage space. So a better approach is to make the problem as easy as possible for the algorithm. And this requires a little bit of thinking. This is human intelligence here. So what information does the problem require? As I said, we don't necessarily know entirely, but we do have some ideas. What pre-processing or featurization would best present that information? I'll explain what those terms mean in a minute. And of course, matching the algorithm to the data type. So what a machine learning system actually does in terms of what it does with your data, it takes in the data that you've gathered, and it has to learn which bits of that data is the actual useful information, the signal from our data set, and which bit is the unnecessary information, the noise. And it discards the noise, transforms the useful information, and often this does involve a dimensionality reduction, interestingly, in things like neural networks. And only then does it develop the model to answer the question. So the main thesis of this talk is we can make this a lot easier for our machine learning algorithm by doing a little bit of, like I said, applying human intelligence before we apply the machine intelligence to the problem to help with this, picking out the data and putting it in the right format for the machine learning algorithm. So as an example of how an algorithm might go through this process, I'm going to very briefly go through some dimensionality reduction. So I said our data is multidimensional, and that's quite hard to deal with. So bringing it down to a lower dimension is easy. Sorry, makes it easier. So if you look at this picture here, you can see the object on the right-hand side is an interesting three-dimensional object. It's obviously complex. It has some structure. It's not entirely clear what it's supposed to be, other than a 3D printed object. But as you see, when we project that data from 3 dimensions to 2 dimensions by casting a shadow, we can see that it is a QR code. So this is the sort of thing that we might do as a pre-processing step for machine learning algorithm. So I'm sure many of you have come across principal component analysis, and this is one of the things that you use this for. So in this example here, we have some data from wine. Okay, so this is analytes of different types of wine from 3 different vineyards, and you've got 13 different things that you've measured, so you have 13 dimensions to your data. And what you want to know is which wine comes from which field, so you're looking for clusters in the data. Now you can't plot your 13 dimensions directly, so how do you approach this? So you might pick 2 that seem interesting and plot them. Sorry, my computer is a bit eager. And you can see here, this is a plot of 2 of the dimensions I picked, hue and alcohol, and I've colored them by which vineyard it came from, but I hope you can see there aren't really any clusters there. However, we use our PCA, we take our 13-dimensional data and we project it down to 2D. And maybe in this, you might say there's 3 clusters. So projection is always going from a high dimensional space to a low one. And then from the pictures at the side, you can see an example of a good projection in terms of it revealing something useful about the object, and a bad projection in terms of the top one. So does this work in this case? So sorry. Yes, so if we take our PCA and we project our 13 dimensions down to 2 dimensions, now the problem is much clearer. And a clustering algorithm is able to actually solve this problem much easier now that we've done this pre-processing. Okay. So what information is necessary for a problem? So I'm interested in molecular machine learning. And the first thing we need to do in that is figure out how do we input a molecule into a computer in order to do machine learning with it. Now, this obviously depends on the task. There's many different ways to do this. So you may choose the SMILE string, which, if you can see my mouse, is this thing here. This is a computer readable and human readable for some people version of a chemical formula. We may also use a fingerprint, such as this thing here at the top, which is just and this is a binary one for whether a functional group is there or not, or a vector of physicochemical properties like molecular weight or number of hydrogen bonds. These are sort of one-dimensional inputs. In this field, we also look at two-dimensional inputs. So this is using molecular graphs. And you may well have heard of graph convolutional neural networks. These are the chemistry version of the convolutional neural networks that were a huge breakthrough in image processing. And then you've got the three-dimensional inputs. And so the one I'm going to talk about later is the grid featurizer, where you basically take a volume of space, break it up into voxels, and take note of which atoms in which voxel in order to input the three-dimensional structure. Now, there's a question of which of these is the easiest to start with, which is the best for the problem. So when chemists sit down to do this, I think a lot of people decide to start with the formula, because as chemists, we're quite used to writing down chemical formulae. We draw them all over the place. It takes less pen ink to write the word ethanol than to draw a picture of it. And we don't even think about this. And so a lot of the early chemistry sort of machine learning algorithms used SMILE strings. And this is good for some things, but I'm going to argue not for everything. So it's a good idea to take a step back here and think about the other neural networks in the world that we know about, and that would be humans. So if you look on the left-hand side of my slide, you'll see a description of how humans deal with data. So it takes a small human 6 months to learn to see three-dimensional space. It then takes them 1.5 years to learn how to convert that knowledge of 3D space into a two-dimensional representation. It takes them 4 years to start being able to write a one-dimensional and symbolic representation. So that I think this points perhaps that three-dimensional is easier for these tasks. So when we ask a machine learning system to take in a one-dimensional symbolic representation like a formula or a name and convert it back to a three-dimensional structure, we're asking it to understand the symbols, convert them to a two-dimensional, sorry, where's my mouse? Yeah, two-dimensional formula like this, and then apply chemistry knowledge to realize those bonds are wrong, and then convert that to 3D space. And the algorithm hasn't had the advantage of having lived in a three-dimensional world. So I'm going to give 2 examples of how I have tried to encode the three-dimensional structure of molecules so that machine learning algorithms can use them. The first one to use in this cool new technique called topological data analysis. So luckily there was a nice introduction to topology in the previous session. So don't know that I need to summarize this, but we're concerned topology is, as I've entirely forgotten her name, one of the previous speakers said, it is the study of shape, and a sort of very strange way. So we count, you can view it as counting the number of holes, it's counting connected regions. So a bread roll is different from a donut. A donut is a torus, it has a single flat hole in it, whereas a bread roll has no holes, for example. So what topological data analysis does, it's a type of persistent homology. I know I'm dropping some terminology in here. That's just in case you know it and you want to know exactly what I'm talking about, but it's not necessary for the discussion. So what we do is we take points in the space, and the space can be any size, and each of those points is a connected region. And what happens is we look at the number of connected regions we have, the number of torus-like holes, and the number of voids that we have as a function of size. So as this little animation shows, we start off with the points, we expand the radii, When the radii of 2 points merge, the 2 connected regions become one. And as we'll see as this animation goes through, the blobs keep merging. And at this point, you'll see these 2 connected regions merge, and then the whole data set is now one connected region, one blob. And this is shown on the rather dramatically named birth-death graph on the right, or persistence diagram, slightly less dramatic. This is a similar sort of thing, only here, once the spheres, the points merge, we end up with a torus, and then this will merge. You'll just see it coming in now. There we go. So this is an encoding of the topological description of the 3-dimensional data set at different length scales. And that's partly why I think this might be interesting to this area, because it works across different scales. And that is one of the things that comes in complex systems, the type you're going to look at. Some more examples. This is a sphere made out of randomly distributed points on the surface. And the color codes here, purple H2 is a void. That's the last thing to die when it collapses. And the ones on the right are the bonds. But the main point is that you can convert these shapes into this diagram. Now, the problem that I have shown this to, or tried this on, is the protein binding problem. So this is about, you've got proteins and they have an active site, and you want to know if you put a molecule in there, so as a ligand or as a drug, how well it binds. And this is used in drug design and drug development. And applying topological features to this is the process of featurization, is very interesting, because what we're doing is we're reducing this structure and this chemistry down to just rather gross shape features. It's very, very simple. So yeah, so this is the process. We take the binding pocket, we throw away all the chemistry. All of the atoms are equal, they just become points. We just have the shape, and then we produce these persistence diagrams. And they're different for the ligand and the binding pocket, as you can see. And from there, we can turn this into some topological features. So basically, there's a way of encoding this diagram here as a set of numbers. So it's literally a vector. It's 36 numbers long. So we do lose a lot of information in this, but what we do keep is something fundamental about the shape of the molecule, or maybe fundamental. So the question is, if we apply this to the PDB binding problems, this is proteins binding to molecules, does it work for machine learning? Is it any good? And this is the answer. So, sorry, I've called it TDAF, that's topological data analysis features. So on this slide, you're looking at the output from a benchmarking system with a couple of different input features. So ECFP, these are fingerprints. This is a list of functional groups. And RMSE is the error on how well the binding prediction. So we want this to be small. And as you can see, using this, we get an error of about 19. Grid features, this was the 3D space chunked up. That one gives you an RMSE of 16. Ignore the GC for the moment. If we look at the TDAF one, we see we get 1.58. So this is really good. So these 3 models and featurizations are the same model. And they're really tiny models. So anyone that does machine learning may well be laughing here. This is a 2-layer feed-forward neural network. This is nothing interesting or fun. There's no real cool maths. There's no convolutions, and it's very small. And you can see the comparison here. The TDAF has only 36 length features and that many parameters, and trains the same in the same time as grid. So it's very, very good. I'll briefly mention the GC features. This is the graph convolutions. This uses slightly more, slightly better maths, slightly more complicated, slightly better neural networks. So it's impressive that this does so well. So then I've compared this to the state of the art on these data sets. And if you look on the left-hand side, most of the models there are models from the literature, and they're very, very big machine learning models, very fancy, lots of parameters, lots of very clever ideas and training and all of this. Yes, and then I've taken the TDAF features with basically the sort of models that I give my third year students to play with. And we are, you know, just with the features competing, if you see what I mean. Because this has had no tuning. The point here isn't to actually beat the state of the art. The point here is to show how far you can get with literally just using the topological data. And if you're wondering about the second one, that's TDAF plus RD kit features. That's where we've added in some very simple chemistry features, such as basically the molecular weight, number of hydrogen bonds. And that's sort of in the middle of the pack. Now, unfortunately, in this field, people don't tend to, well, no one has come up with a nice way of comparing the complexity, I mean computational complexity here, of different models that with completely different architectures and training regimes and all of that to each other. So the closest I can get is the size of the features and the number of parameters and the number of the layers, and not many people report them because the focus is on building a model that's good rather than building the most efficient model. But with the numbers I've got, I think you can see that the TDAF is much more information dense input, and it has grabbed some of the very important information from the data set because it's able to compete with a much smaller, much simpler neural networks. So what's the point? The 3D shape of molecules is important, and for molecular machine learning, we need to keep that. And by using, we want to remove the noise from our data and keep the signal. And by using this persistent homology, we can grab the very simple shape properties and actually, you know, actually get a very good answer on very small, very easy to train networks. Okay, briefly, this is the second method that I looked at to encode three-dimensional structure for machine learning. And this comes from another problem we have in chemistry data, and that is the need for dataset augmentation. So one of the problems with chemical data is that it is small. It's small compared to chemical space. So it's assumed there are 10 to the 60 potential pharmacological molecules possible. I'm sure if we're looking at potential biologically active molecules or molecules that could be part of some sort of interesting prebiotic chemistry, this is a huge number as well. And of these pharmacological models, only a tiny percentage, like 10 to the 15, have been synthesized by mankind throughout the whole of our history. So there's a lot of chemical space that we have not explored. But they're also very small compared to data sets successfully used in ML. I think the previous speaker, Dimitri, talked about this. He showed some of these data sets, so I can skip through this. But MNIST, which is the data set that everyone starts off playing with in machine learning as a tutorial, is 60,000 data points. The sort of data sets we're looking at in chemistry are tiny. So the PDB bind, the protein binding stuff I just showed you, that was 4,000 data points. And the one I'm about to show you now, ESOL, is a data set of solvation. So you have molecules and you want to know how well they solvate. This is useful for drug discovery. We only have 1,100 points. This is a tiny amount. So we look at neural networks. I do other machine learning, but neural networks is my favorite. So we look at how well they have done with this problem. And in convolutional neural networks, in the visual recognition field, this technique of data augmentation was invented. So you want to make as I said, we want to separate the signal of the image from the noise. And what we put into the neural network is the pixels, so the pictures of the cat. And we don't want the neural network to assume that all pictures of cats have like blue at this pixel or something strange like that. So we want to change the pixel space without changing the noise, the signal of the image, which is what is a cat, which is, it's got pointy ears, it's got whiskers. So in the image field, you can do reflections, you can rotate, you can crop. And now you have 4 images that are similar, but different enough the machine could still learn from them. Well, would this work with molecules? Of course not. So what we need to do is we need to say, okay, this is a great idea, but we need to apply some chemistry knowledge. We need to preserve something different. We need to preserve rotational symmetry and chirality. And this is how we do that. So some of the best neural networks around, or at least when I started this work, were two-dimensional neural networks. The convolutional neural networks were the big thing. Sorry. And we want to input three-dimensional objects into these two-dimensional networks. So we want to have, so we want to turn our 3D object into a 2D object. And we choose to use icosahedrons, and icospheres, because they have the minimum distortion. We go from 2D to 3D, which is what these maps are supposed to show you. So I'll go through the technique. So we take our molecule, in this case, cubane, and we put it inside an icosahedron. And now we project from the center to the edge. So if you imagine there is a light bulb in the middle of our molecule, and we cast a shadow onto the outside of the icosahedron. And where an atom hits the outside of the icosahedron, we color that face with the color of the atom. And then we can unfold it. So this is what we get. So if we have cubane and we do this procedure, so we just project, cast a shadow of the molecule onto the surface of the sphere, color in where the carbons are, and unfold it. And we have these weird looking nets, which is triangular pixels, and it is a description of the molecule in a way that we can put into a neural network. Now, there are 60 of these for an icosahedron, so we've achieved our goal of being able to augment our data set, because one molecule can give us 60 training examples. And in fact, many more if you rotate things and the like. It preserves chirality, which is brilliant. And of course, just using 20 pixels isn't going to be good enough. So we can make these things called icospheres. So we add more triangles, basically.
5 minutes.
Oh, sorry?
5 minutes.
5 minutes. Oh dear. Okay. Okay. Right. So quickly, we can, if you look at these graphs, this is the molecule turning inside the icosahedron and the icosphere, and that is encoding something about the molecular structure. Basically, does it work? In the interest of time, I will skip over and say yes. The exciting thing here is that by just taking this sort of approach and then putting it into a neural network with no chemistry either here, we have the mass of the atoms. They're not labeled. It's just that we've managed to equal the ab initio result for this particular data set, which is quite interesting. So I did want to touch on category theory, and I'm going to very, very quickly try to, because the next speaker is going to talk about this more. So I'm going to go very quickly. But I think category theory is something that would be very interesting in this field. It's something I'm looking at now. And it's the main two things that I want to express to you here is that it's a sort of mathematical language that can express other systems like chemical reaction networks, which you all know a lot about, but also very different things like linguistic models and resource theories. And it preserves compositionality. It's all about making larger systems from smaller, and that will possibly be very, very useful in this field. But that was a future work thing, and David Spivak will talk a lot more about this in the next session. So I will finish up there. Thank you.
Are there any questions? Thank you so much. That was a really wonderful talk, really. And I've learned quite a bit. But are there any talks? Any questions? We have a couple of minutes for questions for Ella.
There's one question in the chat by Jen Pang. I'll read through it very quickly. We know that there are some encoding systems that may assign different strings of characters to the same molecule, i.e. the same molecule can have different names. Is your encoding system able to give a unique name to a specific molecule?
That I think has to be investigated. I do know, so there were two systems there. So the The topological one differentiates between conformers, so it can tell the difference between a boat and chair conformer for cyclohexane, but doesn't do chirality. The icospherical one does do chirality. And it's a matter of they would be very close. So I don't know if you noticed with the benzene maps, because of the symmetry of benzene, some of those maps were repeated. So if you had the molecular structure and you pick the size and the size of the icosphere, it wouldn't be necessarily unique, but you'd get a set of nets that would be, that would point to that one. So it's not unique, but hopefully it should avoid you picking up the one molecule. But it's more statistical, as in you're like 120 of these nets are the same as this one, so it's possibly the same thing. Oh, and the second bit of that question, I've got it up. Molecules are dynamical, for example, vibration, rotation, etc. Yes, I skipped over that. So for the augmentation, well, for both, but in the augmentation examples, the second one, some of the augmentations were to move the molecule a little bit. And obviously you can vibrate it as well. So you can do all of that and then encode it and it would change. So you saw the molecule rotating. I could have had the molecules in one place vibrating, you'd get a different pattern.
So unfortunately, we are 1 minute above time. There was another question, but if I may invite the questions for the panel discussion, which will take place at 3:30 to 4 p.m. That would be fantastic. Thank you so much. Ella, I'll pass.
Thank you.
Thank you. Great work, by the way.
Thanks.
You guys see my screen?
Yep.
Yep.
Looks good and stuff, not weird and okay. Shall I start or
I think we should start and then Ella should take over. Okay, just give her.
Yeah, sorry, I was supposed to be chairing this one. Sorry, David, please start.
No, it's okay.
Okay, well, thanks for having me. It's very interesting, and I hope that I aimed this talk correctly. It's not like the previous ones, but yeah, here goes. So I want to talk about dynamic organizational structures, and I tried to kind of get a sense of what the what PCE3 is. But I often start talks these days with why am I here? So I think the question of what has brought us to this moment here is always relevant. It's always a good starting point. And there's lots of lenses for it. So physically, you could ask, you know, out of all the positions that all of our physical atoms could be taking, why are they collected here in the body that's me? And why are we all here on Zoom? And like, why is that happening? It's kind of amazing. Or culturally, you could ask, why were these people invited or funded to be at this together? And finally, personally, what is our motivation, my motivation or whatever for being here? And so to me, I mean, somehow physics is all of our motivations and all of our funding and all of money and everything is implemented in physics. At the end of the day, we believe that, you know, it seems to be that material, that all this is reflected in matter. And so I think for me, like to understand where these motivations and this collecting of things come from, I've been interested in the origins of life. I'm a mathematician, so I don't know much, and mainly I was just inspired by Eric Smith videos, if you know who that is. And I'm just going to, I apologize for any misconceptions I have. So just take all this as my impression and not like a very hobbyist or deeply interested in this stuff, but only able to understand things when I can make it mathematical in my own way. So this is just my own rendition. And my rendition, so that you know where I'm coming from, is that proto-life, maybe in deep sea hydrothermal vents, was like a minimally complex lab that could perform certain exothermic reactions, like taking CO2 and water and making methane. and that life basically develops and maintains the equipment for dissipating free energy. We are a little lab that walks around and does that. And so we're here at this meeting to collect materials like knowledge that we're going to use for that sort of purpose. Eventually, it'll make its way into funding sources that extract, more efficiency from the sun or from whatever. And somehow this funding is like a siphon where you got water on the top of the hill. You want to get it to the bottom of the hill, but you have to suck a little bit on the siphon to get the thing going. And so I'm really trying to understand just the simplest idea of like, how can we demystify some of the things we see around us? Like, and how do you get kind of a multi-scale approach for thinking about those things? So I'm fascinated by nature's capacity to have developed things like us, and we came from prebiotic chemistry. So how is this development happening? How is the top-down problem? What is the top-down problem? Is it something like there's too much free energy, or the sun's hot and the surface of the earth is cold, and the core is hot and it needs to dissipate those derivatives? What is it that we should be thinking of? But whatever it is, I'd like to make these ideas formal and systematic. So to give you some background, the way I think about mathematical fields is that they're accounting system, high fidelity accounting systems. So arithmetic is a mathematical field. And what do you account for? You can give an account of the flow of quantities, like in finance. So the auditor comes and says, hey, what's this $12.43? And you give them an account of that using arithmetic. You're not questioning that system. You can be questioning what's written in the system. And similarly, in quantum mechanics, you want to understand elementary particles. How would you give an account that a physicist would consider reasonable? You would use Hilbert spaces, for example. Or if you wanted to understand why someone's winning at poker, how should the account be done in a formal, in a way that people can trust that all the interesting stuff is like in the translation between math and the world we see, rather than in the math itself. Well, we're going to use probability distributions because those are very well understood mathematical things that help us account for likelihoods. So what's the rules for why would you need math? Because an account of phenomena, if you really want to coordinate across long time scales or distance scales, you need to be writing in a high fidelity language where you can have faith that it means what you think it means. And so you need to understand the phenomena and you need to track certain relevant variables. So the language has to articulate and kind of give you the joints to see relevant type differences. And then below, I'll explain what I mean by type differences. And the language has to provide operations that correspond with with the interactions between those types. So what am I saying about math here? Well, let me say it in finance. So in finance, there are two different types. Let's say there might be many, but let's just look at two. One is dollars and one is quantities. Now you can add and multiply numbers, quantities. You can have 5 boxes and 10 more boxes and get 15, or you can have 5 boxes by 10 boxes and get 50, or 10 widgets and get 50 widgets. If there's 10 widgets in each box. But you can also multiply dollars by quantities and have 100 things at $3 each and get $300 for those 100 things. But you can never multiply, as far as I could imagine, a dollar figure by a dollar figure. It's not a relevant operation for that type. $3 times $5 is not a certain thing that you would be interested in. And so from a mathematical point of view, you might say that dollars are forming a vector space, or maybe things of value are forming a vector space. Maybe love is a different dimension than dollars or something. But the point is, I don't know if you can scale love, but you can scale dollars, and you can't multiply dollars by each other. And so the point is to kind of, to have a high fidelity language of finance, you might want to protect in your spreadsheet for people multiplying dollar figures. That could be like an add-on. Category theory is the accounting system. So I said that all mathematical fields are accounting systems. You can believe that if you want. It's what I see as the case. So if category theory is a mathematical field, then what does it help you systematically account for? And the answer is coherent structures. So we see coherent structures all over the place, just like we see likelihoods and finance all over the place, or flows of materials all over the place. If you want to talk about coherent structures, like the fact that there are analogies that really help us think, these similarities of structure. If you want a high fidelity accounting system for analogy, then that's what category theory is for. So it's been useful for creating analogies that are used, in the most famous modern mathematical. If you ever like read a quant or whatever article about math, Langland's program or whatever, they're always using category theory these days, more and more. So, but it's not only been useful in math, it's also been useful in programming languages and physics and material science, linguistics, et cetera. And so what I think we're interested in is if we want to understand prebiotic chemistry and the evolution of the early Earth, we want to understand like what sort of structures are useful that we need to track there. And again, yeah, please excuse my ignorance of PC3. So this is how I naively see it, that our concept of the early Earth is that it formed from like that life on the early Earth, let's say, it was formed from chemistry. And I'm seeing at least a repeated pattern regarding concentration of power. And I want to define power, X's power, to be its capacity to quickly catalyze a change in conditions. So in physics, power is work divided by time. But more colloquially also, the power to birth a child is like a 9-month catalysis that you make an amazingly structured object, that in 9 months of work where you have this kind of zygote and food and you catalyze, the woman's body catalyzes a baby out of that. And if I detonate a bomb, then I also quickly catalyze a change in conditions. So I'm saying that that life catalyzed certain chemical reactions on the early Earth. And the reason I like this point of view is that I think I can get rid of the entity called survival, because catalysis, when something catalyzes, it does remain there after the thing is done. So there's no bomb that isn't detonated. Hopefully, when the person detonates the bomb, the person's there on the other side of it. I mean, we don't like when they do that, let's say, but they are catalyzing in the sense that the detonator is still there afterwards. Otherwise, it wasn't a very powerful move. And birthing a child, we also hope that. So I'm interested in survival as basically like a catalyst for making change in the world and life as that. And I'm really curious about why these catalysts keep concentrating in terms of their size. So transistors are tiny objects that are both close to the atomic scale of matter. They're what are they, 40 nanometers or something, but they're also close to the atomic scale of pattern, in the sense of like they're half of a NAND gate, and NAND is the basic structure of logic. So somehow, maybe that's not, there are many, many examples where power concentrates, whether it's a bomb or, DNA or whatever. We get like coded language that can set off huge differences. And like, I somehow wonder like how this keeps happening. So is there a theme to the sort of changes that life catalyzes, and in what respects were the material conditions on the early Earth relevant to the ability for power to kind of keep concentrating? Like there's a tremendous amount of power in Jeff Bezos or the president of the United States, but that was something that had to be developed. And somehow that was developed by physics. So I want a multi-scale version where I don't have to go all the way down to physics to help me see how power keeps concentrating in organizations in society or in bodies or whatever. So dynamic organizational structures, that's the title of the slide, but that this concentration of power comes from organization, not elementary makeup. That's kind of I'm going to be getting into compositionality, which is what Ella mentioned category theory is about. And so I want to say that it's really organization, not the elements, not titanium. Like, so spider silk is stronger pound for pound than steel is. But spider silk doesn't have to be mined or smelted or anything. It's made by a spider and using flies. So what it is, the strength of it is not that it comes from these amazing elementary materials like titanium or some fancy thing that you need to mine from somewhere, but instead that you have this hierarchical organization, and that's what's so important. So any life form is a collective dynamic organization of smaller parts, as far as I know. And it's the organization of the life, the ribosome and the nucleus and all the different things in the right place. It's that organization that provides the power. Now, I want to note that what happens during these organizations can change them. And as an extreme example, if what happens causes death, then the system would disintegrate. Or a CEO might see what's occurring and change the company org chart. This is something that I think in PCE3, we're going to need to be very cognizant of, that like what happens within a little boundary area we're looking at can change the org chart, can change who's talking to who, change the pattern of interaction between what's going on there. And so what I'm trying to provide in this talk is very short, but is an accounting system for these ideas. So basically, they're going to be open dynamical systems that interact with each other. And they're doing so according to some pattern where, like at a given time, only certain materials and signals can flow between them. But because of those signals, they might change their interaction pattern. So I'm going to talk about a category theoretic accounting system for these things. And I'm not going to assume you know any category theory, I'll just draw pictures. But so during the remainder of the talk, I want to discuss open dynamical systems and interaction patterns and try to explain that, explain dynamic organizational structures, and then just conclude. Okay, so when I say an open dynamical system, it's a kind of worker. It can interact with the outside world through a specified interface. So for example, I have an interface, and I'm able to communicate outwardly with the position of my body, how my vocal cords are vibrating, all sorts of stuff like that. And so that position of my body, including the position of my vocal cords or the way I'm shaped in the current moment sitting down, is part of my interface. But I also can receive forces through my body. So based on the position that I'm in, you can apply forces to me. You can send me signals. Things can come in through my eyes, and I call them these forces because they affect my state. So I have this internal state, the forces and signals coming in change that state, not just like by fiat, but based on what my current state is. So if I'm happy, the same signal may change me differently than if I'm sad. But that state changes based on forces, and those I'm in a new state now, and now I display a different position. And so so that's kind of the open dynamical system. You can think of these as either continuous or discrete. So either one's fine. In both cases, the outputs are a function of this current state. In a continuous ordinary open dynamical system, the state evolves according to some ordinary differential equations, and the inputs provide time-varying parameters. So you can imagine a vector field, but the inputs to the system are changing the vector field. You could look at those little lines in the chart, like imagine a vector field and just imagine the little line segments changing based on what comes in. So in a discrete version of an open dynamical system, the state just updated almost like on a clock, just tick, tick, tick. That can be easier sometimes for modeling if you don't know the differential equations, but you just kind of have a Coke machine, or you have something where you say this, then this, then this, and this is how this affects it, like more like a flow chart. So, but what I want you to be able to do for this talk is to visualize these interfaces, because we're going to think of things in terms of interfaces that are being inhabited by open dynamical systems. Now, these interfaces can change through time. For example, I can open and close my eyes, and what comes into me is changing. But at any point, we are going to draw that interface that's housing the open dynamical system as a box with inputs on the left and outputs on the right. So maybe you're getting auditory and visual signals coming in on the left of this box, and then on the right, you have body position, leg position, vocal cords, etc. Okay, and then these open dynamical systems interact with each other in interaction patterns. So you could easily visualize this sort of thing, a wiring diagram, and you can see that P1 through P5 are little interfaces, each one possibly housing an open dynamical system. But let's just leave those inside for a second. Those interfaces, P1 through P5, are interconnected inside of a boundary interface Q. And so if we think of that thing phi, that wiring diagram there as phi, from P1 through P5 to Q, then that phi is itself able to give rise to a formula. And that formula would say, if you pop a open dynamical system into P1 through P5, I will be able to tell you the resulting open dynamical system in Q. And then you can add that to your library and take it with you and just think of Q as a 2-input, 2-output dynamical system. So in category theory, that phi thing is called a morphism, and it's a formal object. It's not a picture. I can draw it as a picture, but it comes with a fully unambiguous semantics in the theory. So that's a requirement, and it is the case. So these wiring diagrams and their ability to nest, which I'll talk about in a coming slide, have been implemented in software. This is not just a mathematical theory, which category theory, being so abstract, is often considered to be theoretical, and yet it's also very easy to implement. And so we'll talk about, well, I wouldn't say overall it's easy to implement, but the things I'm talking about today are. So now interaction patterns can be more general. You might have weighted connections. You might have dynamic, it might be changing through time, might be probabilistic, which signals arrived from P1 to P3, et cetera. Those are harder to draw. So I just wanted to draw the simplest wiring diagram. But the point is that no matter how you talk about interaction patterns, whatever you want to do with them, those as far as I can imagine, those will have unambiguous category theoretic syntax, and we can talk about that if you're interested. So interaction patterns can be nested. Again, they're much more general than wiring diagrams, but wiring diagrams are the easiest to visualize. And I want you to, when you look at this picture here, see 8 interfaces and 3 interaction patterns. And the 8 interfaces are P1, P2, P3, P4, P5, but also X is an interface. That X is not the wiring diagram there. X is supposed to indicate the 2 input, 2 output outer shell. And Y is supposed to indicate the 1 input, 2 output outer shell. So that makes 7. And then Z itself is a 1 input, 2 output shell. So we're seeing 8 different interfaces in that picture and 3 different interaction patterns, the stuff inside of X, the stuff inside of Y. And then with those kind of abstracted out, just seeing X and Y inside of Z. But then we can nest that, we can compose and say, yes, it's true that cells, you have 2 cells here, and then, or you have a bunch of cells and they form a tissue, but inside of each cell is also some organelles or whatever. And we don't have to draw the boundaries in it. Like, we can kind of abstract away those boundaries and still get the same answer. It doesn't matter how you draw the boundaries. What matters is what's flowing. What matters is the parts and how they're interacting. So the point is, you can abstract, a population of open dynamical systems as an open dynamical system. Like the brain may consist of neurons, and center, different parts of the brain, V1, V2, V3. But the point is, you can put them all together, and you don't have to keep those boundary lines and no, that's not V1, that's part of V2. That won't matter, because how you draw the lines is not the important thing. The important thing is the feedback loops and the connection patterns. So in the above pictures, the interaction pattern looked like it was fixed, and that works great for integrated circuits, but it doesn't work for real life. And like, even computers are plug and play. The point is, the wiring diagram and who's connected to who is changing. And we're on this Zoom call now, but later we'll disconnect and cells can swim around. So the point is that the interaction pattern changes through time, and the signals that are received may cause, if Ella says, okay, go ahead, like that signal causes me to unmute and begin talking. So that sort of thing needs to be modeled, because I think on the early Earth, like, there's no way that you're going to just see some fixed interaction pattern for all time. It's going to be based on the stuff flowing in that interaction. So the interface of every open dynamical system could change through time. As I said, your eyes might be open now and closed later. The car is receiving in GPS now and not later. And so your system interface depends on the mode. And so in this category theoretic accounting system I've been talking about, the formal system behind it is called polynomial functors. And if you're interested in learning more, that's a subject that is a well-known subject within category theory. But the point is that these open dynamical systems are in time-varying interfaces, like a protein that's folding, and certain parts are exposed at some points and not exposed at other points. And how you're allowed to interact with me depends on how my interface is exposed to you. So that's a really important aspect of a lot of this stuff. And that's something that polynomial functors and category theory can help us make very clear. So by dynamic organizational structure, and someone joked that maybe we should call it a multi-scale dynamic organizational structure, if you see the joke, is a systematized version of all this stuff. So it's like a presentation of the laws of nature or the rules of a certain game. And it tells you these rules are about how parts are allowed to form into wholes, and that they need to do so in a compositional way. So we know of a zoo of simple examples, but we only, like, this is kind of a new idea, and we only know of 4 interesting ones so far. And the ones we know are deep learning, convolutional. I don't know all the latest things, but the vanilla convolutional recurrent neural network stuff fits into this story as a dynamic organizational structure. Hebbian learning, by which I mean a kind of simplified version so far of spike time dependent plasticity, where if you fire just before I do, and we have a similar valence, then I want to wire to you, thinking that you're a good predictor of what I'll care about. Prediction markets are another example of a dynamic organizational structure where things have varying wealth, and that wealth lets them kind of influence. Well, each one predicts what they think is going to happen and has some weight behind them. And also non-cooperative strategic games. So in each case, where people are playing games against each other, and having Nash equilibrium and that sort of thing. So in each case, a systematized dynamic, there's some sort of systematized dynamic for how parts form wholes, and I can't explain that super clearly here.
David, sorry, you've got about 5 minutes left. So okay. There would do questions after, but just to give you a 5-minute warning.
Yep, thank you. So in this picture, right, parts form wholes, but in dynamic organizational structures, there's the pattern, the wiring pattern is generalized. You could have weighted sums, like in deep neural nets. The interaction pattern is dynamic, so like the weights and biases can change. The wiring pattern you see there, maybe P1 would disconnect from P2. And it's formulaic and compositional, and that doesn't appear to be in that picture there. Like, what's the kind of formula for how that got to be? It's hard to tell. But like this formulaic and compositional aspect shows up in deep learning. Namely, you have gradient descent, and if you have a population of gradient descenders wired together, they form another gradient descender. In prediction markets, the wealth updates based on Bayes' rule, and if you have a population of predictors, each one with a varying amount of trust, you could get a prediction from that by aggregating those predictions. And then as you update the wealth based on how well everyone did, that is compositional with respect to forming subagents. So it's this compositionality with respect to forming subagents, that's the point. And the application to PC3 is that for me, I'm disappointed, like everyone's so in love with Darwin, and I wish I could be one of them, but the individual is metaphysically primary, and it really bothers me for creating a theory that I can understand mathematically. So it causes people to have to argue about whether groups can be selected for, because it's all based on individuality. What is the individual? Well, a group can't be an individual. That's kind of a discontinuity in the theory. And in organism learning and adapting, what's going on inside of them, that to me is a selection process, just like birth and death. It's a selection for which moves I make are useful. And I find these discontinuities in the theory really a place where we can improve. So the individual shouldn't be baked in. I think in prebiotic chemistry, the boundaries would be much more fluid, and the theoretician would need to be able to constantly change them. For example, you might say that low latency feedback loops are what makes me an individual rather than my skin boundary. So I think that the theory, if we're going to really get to an accounting system for prebiotic chemistry, we shouldn't have to like come up with ad hoc boundaries for every single case. So the above stuff I've been talking about makes this accounting system for open dynamical systems that inhabit interfaces, and is compositional, which continuous with respect to boundary drawing, and individuality is a derived concept rather than being metaphysically primary. Parts can connect or disconnect based on what occurs during that interaction, rather than somehow being stuck because they're part of this one thing called an individual. So to summarize, category theory is an accounting system for coherent structures, and it helps you structure, take care to think clearly about what you're trying to think about. It can think about quantities if you want, but it naturally thinks about relationships. Quantities would just be seen in terms of their relationships. And its operating principle is compositionality, that nothing really exists by itself. Dynamic organizational structures are category theory accounts of interacting open dynamical systems. So we all know they interact with each other. We interact with each other. We send information and signals and materials to each other. And these interacting parts form wholes. Maybe there'll be a white paper that comes out of this. And this pattern changes through time, who's on the document or who's listening to who. Now, we only have 4 known interesting examples of these dynamic organizational structures, but I'm sure there's just tons more. And it just takes creativity to find them and then to extract them into this language. So I think that prebiotic chemistry and the evolution of the early Earth may offer a really, really cool one. That is the one I would probably find the most interesting and important. I'd love to understand a system for how identity flexible evolution works. And the math gives guardrails like compositionality that ensure the integrity of what you're doing, that isn't going to kind of stop halfway through. So email me if you'd like to explore more about this. Thanks.
Thank you very much. Are there any questions at the moment? If people want to put their hand up. Go on, Zach. I saw it pop up. Do you want to speak?
Yeah, this can be later on. But you really touched on this very lightly. Does this formalism, offer a more comprehensive alternative then to the ambiguities that are really inherent to this kind of multi-level selection theory, or just characterizing systems as being subject to multi-level selection?
Yes, I would. If I tried to write selection down, whatever, in a dynamic organizational structure, this is like a trademark word or whatever, like it's a keyword. I would be forced to have the person be able to explain why, how multi-level selection could work. Why there wouldn't be one level at which it would be working. It'd have to be the same principle throughout, and there would be kind of this compositionality as a fully formal. Just like multiplication, there's only a certain way you can do it for it to work. There is only you can do Hebbian learning and deep learning and prediction markets and in games. There's tons of different things that can fit this, but if selection is to fit it, it has to be compositional. We have to understand how it doesn't matter. It has to be multi-scale for it to even make sense. So it would be guardrails I could use to have a discussion with someone where we could see how that is working multi-scale.
There's a question from Hank Rainwater. Do you want to speak?
Yes, the question I have is if you apply the category theory to cellular automata in which the rules are well defined.
Yep, that works really well. It's certainly a good case of this sort of thing, and polynomial functors as a formalism, for example.
You got any references for that?
References? I could send you slides for it. That I usually my slides have like almost all the details. And not in these, or my math slides do. So I could send those to you. Yeah.
Okay, that'd be great.
Sure. Would you send me an email if you don't mind?
I will. I see your email at your last slide, so I'll send you an email.
Great.
All right, thanks.
I have a quick question. So the word interface sparked ideas in my head. Basically, the level above prebiotic chemistry, which would have to be included in a multi-scale level discussion of life and selectivity, is cells, and cells are all about interfaces. You touched on that when you mentioned sort of organelles and mitochondria and cell boundaries. It seems a really nice way to sort of explain the operation of information flow through cells and life in that sense. What do you think? Can you say more about that, please?
Yeah, that's definitely my hope. My hope throughout doing this sort of thing was that I'm always seeing parts forming wholes. And at first I was drawing these sorts of pictures, wiring diagrams with like control, thinking of these things as like control theory systems or integrated circuits or whatever. And then I realized during a NASA project where we were trying to do safe separation of airplanes, that we really had to make sure that what was being sent between them could change the wiring pattern. And so that's kind of what I was talking about here. But yes, certainly, like whether it's neurons in a brain or organelles within a cell or any of that stuff, the interest here, the thing I'm trying to account for is that we do see larger wholes being formed from smaller parts that are interacting, and that sometimes those interactions can change based on what's flowing through that interaction. Interfaces is a way of just kind of making your own, there may be better interfaces and worse interfaces. It may be that you don't, that certain ways of grouping things are computationally more efficient. It'd be very inefficient to like group my eyeball and your ear as like one thing, that no one would ever want to use that object to think about anything. It's much more efficient to collect things together when there's like lots of low latency feedback loops. But the point of interfaces is to be able to kind of control that part of the story and have it be a formal mathematical object as opposed to just something you write down in text.
Yeah, okay. Another quick one as well. The concentration of power, which you touched on at the start. So I wonder if that's, well, I was talking about efficiency in neural networks. I'm wondering if that's a measure of trying to make the system more efficient by concentrating power to smaller objects. So instead of and it's the opposite perhaps to compositionality or flowing the other way. So we've got the big system and it maybe optimizes by making the smaller chunks more powerful. Maybe we lose things, strip things off.
Yeah. Somehow, like when things are being repeated over and over across many long distances, there seems to be some urge to centralize it, and then just kind of copy it out from there. I don't know. It's really interesting to understand, like, to see why this keeps happening. I mean, when we're making neural networks more powerful, it's happening because of motivations from funding, et cetera. And it's just kind of, how is all this coming together?
Is there any last questions? Okay, thank you very much. Hopefully you'll be able to stay around for the end and we can chat further. I've got many more things we can say about category theory, I think. But our next speaker is Claudius Gros. Professor Claudius Gros, are you here?
I think he may be muted. I saw his lips moving.
Yeah, we can't hear you.
Okay, sorry. First unmute and then sharing.
Okay, take it away. Thanks.
Okay, you see my slides?
Yes, we can.
Okay, it's a pleasure to talk here and thank you very much for the invitation. And this is kind of a brainstorming talk. So I want to vent an idea with you, and this idea specifically whether the so-called strategy of the commons has some relevance for the prebiotic life. And let me just outline what I'm going to do. Since this is a relatively high-level concept, I will give a very short introduction to another high-level concept, the example of hypercycles, and to put my point of view why sometimes high-level concepts can give you some qualitative insights or notions. And then I will come to my main point, to the strategy of commons. I will point out that something interesting may happening, and namely entry barriers in a competitive environment, and maybe that is may be very important also very early on. And since this workshop has a title From Nano to Cosmos, and there has been a relatively little cosmic scale, maybe in the end, if I have time, I make two comments on somewhat related or unrelated cosmic issues in this concept. So for my introduction, just a very short recap of what the notion of hypercycles is or was. That's a notion originally developed by Eigen and Schuster in the 70s. And the idea is that you have small cycles of chemical reaction which can autocatalyze themselves, but they can also have an influence on other small networks and enhance their catalyzation or their reproduction. Nowadays, we probably wouldn't talk about hypercycle, but just talk about biochemical reaction networks. There's no need actually to have a ring, kind of a cross fertilization. And the standard model is like this one. You have concentration of some chemical reactants, Xi. They have an autocatalytic rate, very on a high level description, lambda I, you have cross catalytic rates, and you have a flux which serves to keep everything in a steady state. Now we'll just show you, just for an illustration, a special case which can be solved analytically, so rigorously. So all cross correlations are identical, apart from the diagonal elements, and we have just some spacing of the autocatalytic rates. And so that is the result here on the right-hand side. Here on the x-axis, we have the species, the reactants in this reaction network. On the left y-axis, they are autocatalytic rates. And on the right y-axis, we have the steady state concentrations once we have self-consistency reached. And now we have two different curves depending on how strong the cross-correlation is, the cross-catalyzation is. If the cross-catalyzation is very strong, the blue curve, we have a larger range of surviving molecules. Otherwise, we have a shorter range. Now, the key point is, so that's why this concept is maybe useful at all, is that you have a transition. You have a clear-cut transition between what is in and what is out. So we have steady state concentrations which are greater than 0 and steady state concentrations which are exactly 0, so which are not part of what is then called maybe a quasi-species. So this would not be the case. So if you have just a generic reaction network, and in the steady state, all kind of concentration would be finite. Here's a little bit larger, but here finite. It would not have this interpretation of a quasi-species, but that you can distinguish between an in and out. So I'm just saying that as an illustration. It is not just as this concept of hypercycle, that's some kind of cross autocatalyzation, but that as a result, you can get the possibility to distinguish between in and out. So that's an example of a high-level concept or insight you could get. Okay, so that's what my introduction. Let me come to the strategy of the commons. It's an old concept, and it is dealing if you have a free resource like this pond, village pond. Everybody, let's say, can go there and go fishing. You don't have access restriction. Everybody can go. And the question is, what happens? Now, normally, you may say there's an overexploitation, and normally that will happen. And this is relevant to many, many different settings in human and also societies in biology. Now, if a common resource is free, it doesn't mean there's no incurrent cost. For example, here you have to buy the fishing equipment. You have to make an investment to exploit the resource. And you also have opportunity cost. If you're sitting here and fish, you can do something else to earn money. So there are always incurring costs. Now, there's been a long-term dispute regarding human societies. And Garrett Hardin in 1968 did write a science article, a little bit philosophical one, saying essentially we are doomed because free natural resources will always be overexploited and will lead to the very bad state of the environment and in the end for human societies. That was questioned, especially by Elinor Ostrom, who won the Nobel Prize in Economics in 2009 for this work. And essentially, she went around and did field studies and found that in many cases, especially in smaller environments, there was a pretty good regularization of common resources, and overexploitation was avoided because humans sat together and decided to do a regulation which normally worked fine. And so that is, of course, on the local level. Nowadays, on the global level, we may not be so sure that this is also holding. Now, since this is so important subject, there has been plenty of research. And essentially, all research now up to now was, how do you avoid the tragedy of the commons, essentially via regulation or cooperation, but the key is how to avoid it. And so lately, I looked at this problem again, and what I did was actually not trying to look how to avoid, but just to work out actually how does the equilibrium look like. So since it's a game theoretical setting, how does the Nash equilibrium looks like? And the result is that the equilibrium is actually highly non-trivial and has some very interesting properties. And I believe that some of these properties may be relevant here also for prebiotic settings. So now regarding biology, it is of course tempting to say any state like this, we have gnus and zebras grazing on a savanna, is descriptable by the trilogy of the common because they have a common resource, the savanna, and which is exploited. But it's actually often not so easy because we have actually not a uniform resources, but normally we have different kind of grasses, and actually zebras often eat something else in the gnu. And then we have predators, which keeps the total population down, even if this picture doesn't really look like predators have a large impact. Now, in prebiotic evolution, it might be simpler. The example here is a lost city type of deep ocean thermal vent, where we have only a few homogeneous resources and which are exploited by possible prebiotic life. So the chemical reaction networks need these resources to function. And most probably, initially, we didn't yet have predators because the prebiotic life was happy to survive at all. So in this sense, the prebiotic evolution might be the ideal application actually of this concept of the trilogy of the commons. Now, the basic framework, I will give you a concrete example. So we have a number of agents, let's say hypercycles, and which invest metabolic energy or time into exploiting a common resources, and xi is the amount of investment. And then they get a return, and the return is determined by the state of the resources. So more people invest into the resource, the productivity of the resource will go down. Now we can have different functional dependency on the productivity depending on the total investment, so how many agents invest. Here I choose an exponential decay, but all the results I'm showing you are valid for any kind of productivity function, which is the state of the resource. So what you could do is per investment cost, you get a return here, but from this return, you have to deduce the costs you have, and that is your net gain. And this net gain you can use, let's say if you're a chemical reaction cycle, to power all auxiliary processes. So all the results I'm showing you is mathematically rigorous. There's no approximation involved. So so this is here again a little bit possible conceptual application. So that is, for example, if you would take this lost city setting, that would be the concentration of, let's say, H2 or so outside of a micropore. Let's say in any of these micropores, you would have your chemical reaction cycles, and the investments you would have, maybe the catalyst you have inside your pore, you need to make use of the resources. And then you have a net gain, and that net gain you will use to power supporting reactions. Now, humans are supposed to be selfish and maximize their own gain. And in chemical reaction networks, that is of course not identical concept of selfishness, but one can argue that maximizing the gain is more or less equivalent to maximizing this output, and that will naturally occur in some circumstances. So the solution is actually very simple. One can do that analytically. One gets a self-consistency condition for the mean as a function of the mean costs of all participating agents. One gets the total investment, and the total investment depends on the mean costs. And when the mean costs are large, the total investments are small, and then the rest. Now, the important thing is that the Nash equilibrium depends on the number of agents. and it's not size consistent. And the second important point is that even if you have an infinite number of agents, an infinite number of people who want to exploit the resources, the total investment will be finite. And that means the state of the resource will also be finite. So the resource will not be exploited to infinity. Of course, exploitation will be very large if the investment costs are small, but not to infinity. And the reason is because of the incurring investment costs you have. So what you can show is something pretty interesting, namely that's the net gain you get, so the reward, so the net gain after investment, it's a mathematically rigorously quadratic function of your costs. So if you have different species, let's say hypercycles or probiotic alive, you have different metabolic costs. If the metabolic costs are too large, you will become extinct because you will get a negative payoff. So your negative net gain, and then you die. But the important point is that this is a quadratic function, not a linear function. And that is due to the self-consistency of the Nash equilibrium. It's a non-trivial result. And this has some important consequences. And the consequence is, it's called here catastrophic property, is that the net gain is dependent on the number of participating units or agents, and the net gain, because of this quadratic dependency, goes down quadratically with a number of participating agents, not like 1 over n. I mean, naively you would think we have a finite resource, you divide it by n people who want a piece of cake from the result, and what you gain will be 1 over n. But that's not true, because you have a balance with your investment cost, and this balance is very tight. So if you balance that with your investment cost, actually your net gain goes quadratically down. And so that means for evolutionary perspective, there's a very, very strong evolutionary pressure, because if you go back here, the net gain you have to survive, it becomes extremely small because it's quadratically small. So that means if you have the pure strategy of the commons, you may be living at the edge of survivability. And that is consistent with a very famous hypothesis, the green world hypothesis. Namely, if you look outside your window, depending where you are, you may see a flush vegetation and plenty of forest. And why is it the case? Why is it not? Are there not herbivores which all eat as much that the vegetation becomes very little? And the famous example where this happened is the Yellowstone National Park, where the wolf had been extinct for quite a while in the past. And then the elks multiplied because there was no higher trophical level. And the vegetation, the aspens, the trees became very diminished. And so that is the example of a tragedy of the commons, a very, very depleted state of the common resource. Once wolves were introduced, this is a picture from a field study, the elk population was reduced and the vegetation recovered. And I believe that this middle picture here may be relevant for prebiotic life, because if you don't have higher trophic levels, prebiotic life will be living at the edge of survivability. Now, there's another point is that we assumed here linear costs, but that may not be the case. Your investment cost in the commons may be nonlinear. Let's say the human example, the fishing pond. If you buy 10 fishing rods, you may not pay 10 times as much as for a single one, but maybe only 5 times. So you may have an economy of scales. And That may be also the case for prebiotic life. Now, I will, and this is an important point. Now, I have here a very specific parameterization of the cost function. I will not go into the mathematical detail. It's very, very simple. Just show you the picture. So the per unit cost of your investment can be either linearly, this is the orange curve, can be actually convex, it's a negative economy of scale, or it can be concave, then you have a normal economy of scale. So we have a parameterization, and we can examine the Nash equilibrium of the talk, strategy of the commons, as a function of the functional dependency on the costs on investment. So whether you have convex, concave, or linear. And the result is pretty dramatic. So that is the investment per unit cost. So these points are different individuals, which are part of in the Nash equilibrium. So they're more, every point is in the surviving individual. And this is for 3 types of concave, they're all concave cost functions. And if the economy of scales is only weak, you have a normal linear investment cost, which then leads to a quadratic net gain. So that is what I call happens then the precondition of having catastrophic poverty. But if the investment costs are strongly concave, like here, we have a completely different situation. Namely, we have an edge of survivability here. Now I'm going to show you that it's more larger. So that is investment as a function per unit cost. You have an edge of survivability. So if your per unit costs are larger, you go extinct because the flow goes here to 0 investment. So then you don't invest into the common resource and you don't get any gain. But that is now what is called a mathematical saddle knot bifurcation. And you have a finite return even close to the survivability edge. So that is very different to what we had before. And you also, in addition, what one has is an entry barrier, because if there's a newcomer entering the system and the newcomer has an efficiency which is around here, and now it wants to start to grow, now it wants to start to grow, it cannot do it because growing gives you a negative return. Only if you have a certain size, you get a positive return. So there's an entry barriers against competitions. And so having a substantial economy of states that changes the system, your state, not only quantitatively, because it's always good to have that, but also qualitatively. And so the idea I want to vent here is maybe that is a key evolutionary step. Because, as I said, you get a qualitative advantage of having not only quantitative, but also a qualitative advantage of developing a certain economy of states. So if you double your metabolic costs and you get a net gain, which is 3 times as much, you get not only quantitative, but also qualitative gain. That is a protection against intruders and parasite. And since catastrophic poverty is avoided, you have resources for further functionalities. And also, which I didn't put here, since you're living at the edge of survivability with a finite return, you have time to evolve and to become more competitive. So yesterday we had a talk about the evolution, experimental evolution of chemical reaction network, and the issue was, can we evolve reaction networks where different species, quasi-species, coexist? And the result from this consideration would be that is much more likely if these different reaction networks have some kind of economy of scales. So that is, of course, a very early consideration, but that is the idea I wanted to vent. So regarding this part, I want to just wrap up this part and then making maybe one or two cosmic scale remarks. So we don't have this economy of scale. The net gain you have is proportional to the negative minus the square of the metabolic cost, which makes it very, very difficult to live at the edge of survivability. So you have to be much better and far away from the survivability limit. But if you have that, entry barriers are generated, and diverse ecosystem may possibly develop. So, as I said, since this is what I wanted to say about
a quick comment. You've got 5 minutes, so you have 5 minutes for the cosmic stuff. Thanks.
Okay, thank you. Since there was also the idea about going to the cosmic scale, there's an issue which I was always interested in, that I think is maybe relevant, or I think it's definitely relevant to the prebiotic life research. And that is the conditions not only on Earth, but on other exoplanets. There's especially one class of exoplanets, the M dwarfs. So these are stars, planets around M dwarfs. The M dwarfs are stars which are much smaller than the Sun. And most of the stars are M dwarfs. And most of them have habitable zone planets, and plenty of them. And so most of potentially habitable planets are most probably M dwarf planets. Now, apart from being small, M dwarfs, the star, takes initially, when the star is formed, a long time to contract. So the Earth took about 10 million years to contract. So initially, when it's formed, the star, not the Earth, the Sun was very big, and then it contracted relatively fast. But the M dwarfs take much longer. And since they are so large initially, and there are also plenty of ultraviolet light, there's a strong photolysis on the planets going on around the M dwarfs. And a substantial part, if not all, of the ocean, if there was water on the planet, would be dissociated if the hydrogen escape. And the calculations show you can easily a very thick, dense, abiotic oxygen atmosphere before any life could have developed. And so the most common type of habitable zone planet could be these oxygen planets. Of course, plenty of stuff can go wrong. The ocean could be disappearing altogether. The atmosphere could be blown away by the solar wind. On the other hand, there's planet migration. And so the question is, may life originate on planets where there is already oxygen and plenty of oxygen? Of course, the first thing you would think is that late Veneer possibility scenarios are then out, most probably, and probably also certain, like the hydrothermal pond on the surface with dry wet cycles are probably out, but deep ocean scenario may survive. So I just want to vent this idea, which I think it's very important, because most of the habitable zone stars are probably oxygen planets. Now, there could be two outcomes. One is that either, yes, it's possible, and we have plenty of possibilities of finding life, or it is not possible, and we have plenty of planets where there could life, in principle, could exist very nicely, but it could just not originate. And so the second point I wanted to make, that is regards a remark I made a few years ago, which generated quite a bit of reaction in the media, is that in some time, maybe 100 years, maybe 200 years, we will be able technically to transport life to other exoplanets. Now that will be not a big endeavor, but it will be with miniature spacecraft, which can be launched by laser as it's being developed nowadays. It is, of course, highly, highly difficult, but it's not science fiction. Then they cruise at relatively low speed. They will take a few thousand years at least to arrive. There's nothing fast. Then they have to decelerate. It can be done by magnetic sail. It takes also a few thousand years, so it's a very long-term project. And then you may see it from the orbit of the target planet. And then if you're lucky, you could see it unicellular life forms like bacteria and eukaryotes, nothing more complicated. And then you can wait for a few 100 million years and let the evolution do their stuff. So it's nothing for humans, has nothing to do with for human benefit. It's just a theoretical possibility to spread life to planets where they could, in principle, be habitable, but they are not. For example, possibilities are exoplanets, which are not always habitable, like Earth, but only transiently habitable, let's say, for half a billion or a billion years because of the constellation in the solar system. Now, as I said, that will be feasible. Whether we want to do it is a completely different question. And as I said, there has been hundreds of reactions to this in the media, to this proposal that this will be possible. And I just wanted to vent it out here because maybe quite a few people in the prebiotic community maybe also have an opinion on this, whether it's something good or bad to do. Okay, so that is all I wanted to say. And thank you very much for your attention.
Thank you very much. Questions? Okay, I have a question. See, you had the economies of scale and you showed it, I think if it was concave, then that caused, the concave ones gave you sort of a separation so that you weren't living at the edge of survivability. What about the other direction? What happens then?
Well, then you always have what is called here the catastrophe, just catastrophic poverty, nothing.
It falls apart, okay.
Nothing special happens, yeah.
Okay. Are there any other questions? I'm going to comment very quickly then on the Genesis project. I think that would be fascinating, but obviously would need to know whether or not there was life there already. So that I think maybe that's something for this community to find out. If there's definitely no life on these planets, then maybe we seed it just so that life exists if we manage to blow ourselves up. But we wouldn't want to be polluting something that was already going. Yeah, what are your comments?
That is, of course, a problem. So, and of course, you would have to do from the very large distance like we are here. That's always difficult. So you would have to have a spacecraft, which either you sent before or you do from the orbit as possible as it is. Of course, you can never be 100% sure to examine the planet from orbit. But there actually also from the philosophical point of view, some very interesting issues, because this is a project which is not for human benefit, and so we had plenty on discussions on that, and all our ethics in the end is to say it's good if it's for humans. So it's either directly for you, for your community, for the country, for humanity at all, or for the planet where we're living, because we are living on the planet. So human ethics says essentially it's rational if it's good for directly or indirectly for humanity. And if something like the Genesis project has absolutely no benefit for humanity, then some people argue this is not rational and you should not do it. So there are some, one can argue in any direction, but I'm saying this has a very interesting philosophical implications.
Yeah, maybe we can pick it up in the panel conversation. If there's no more questions, I'll move on. Okay, so the next speaker is Juan Pérez-Mercader, who hopefully has screen share working.
Just a minute. I think I have it working. And so. Just a minute. I tried the trick earlier.
I see only a black screen. Oh no, this is okay.
Just a minute. For some reason, this has become extremely slow.
Let's see, Juan, we see your PowerPoint, the overall thing now.
Yes.
We just don't see the thing, yeah.
Yeah, I need to port the PowerPoint and it's not letting me do it.
Hmm.
Let's do the presenter's view, which is what I want to do. I apologize for this. If it's misbehaving for some reason, which I do not really understand.
Oh, now we see the presenter view.
And you should see, okay.
Yeah, we see your view.
Can you see only?
We see screen 1, which is the presenter view.
Yes, you should see screen 2, which is where I am. It's become very, very slow.
Ah, there we go.
Okay,
Are you
cool.
only see? Okay,
We
so
can, yeah.
Go ahead. No.
I was going to say we've got the right view now. Sorry, go ahead.
Okay, so thank you so much, everybody in the audience, and Zach for inviting me and exciting me about this talk, which made me go back into my old PowerPoint files of about 20 years ago, and which I did with great pleasure, by the way, but I had so much information. I had difficulty understanding what I wanted to say, and I wanted to be brief, meaning half an hour should be more than enough. So what I will be talking today about is emergence, as a form of collective behavior and some of the things associated with it. And I will just glance upon various things. And in addition to glancing upon these various things, which are important to start thinking about emergence with the tools of condensed matter physics, which is what I will show. And then I will end up with an application before I give pass to Eric Chaisson with his presentation. What I wanted to do is to make you aware of the notion of emergence and how the notion of emergence is useful in the context of the origins of life. In particular, let me start by giving some definitions that I will give a couple of examples, say devote some time to tell you how condensed matter physics understands this kind of phenomena and the things you can predict with it and how it works. I will probably be able to do a little bit of mathematics, very simple mathematics in the PowerPoint presentation. And then I will tell you how it can be used for prediction and show you an example of prediction actually working in the laboratory. And I will send my transparencies once I give the talk. I will send my transparencies to Zach and Jennifer. And then anybody who wants to look at it, please do and comment anything you want. Definitions. What is emergence? Paul Simon, actually without citing Richman in 1936 work, Paul Simon in the 50s and 60s spoke of emergence as the notion that the whole is more than the simple sum of the parts. That is to say that 1 + 1 is not 2, it's much more than that simple sum. John Holland, somebody who worked on this for many, many years, thinks of emergence as the transformation from the extremely likely to the likely, and is a major characteristic of systems that exhibit emergence. Finally, Phil Anderson, a physicist, and Paul Krugman, and incredibly intelligent fellow and an economist, work and even provided a good definition of emergence as emergence is about how large interacting ensembles exhibit collective behavior that is very different from anything that might be expected by simply scaling up the behavior of the individual units. And in this context, here you have a majestic example of a bird of emergent behavior in the example of bird flocking, where all the interaction between the various birds actually come into play. This is a characteristic of many body systems, and many body systems, there are of course a huge number of them, very different, but they can be classified into what we call universality classes, using scaling and using the renormalization group. And this is what I will be doing in the next couple of transparencies or so, but let me just point out what the phenomenology of emergent systems is. And the phenomenology is associated with the fact that emergence is of certain systems where there are many components in interaction. That is to say, for example, the case of many body systems, there is nonlinear behavior, there is lack of equilibrium, and is observed, of course, in evolving systems. It's associated with the spatio-temporal evolution of the system, and is related to scale changes. And it is here at the point of scale changes and complexity associated with those changes that physics comes in the form of the renormalization group and the understanding of phenomena like, for example, the magnetism, where if you have a magnetic system, a magnetic material, and you take the magnetic material and put it at the so-called critical temperature, like here in the northeastern graph that you see here, you have the number of domains which are lined up, the ones with pointing up, which are the ones in black, and the number of domains pointing down, which are the ones in white, is roughly the same. They occupy the same area. If you heat up the system, then they really occupy, as you have in the northwest plot, you have roughly the same. But if you go below the critical temperature, or you are precisely at the critical temperature, there are a number of phenomena that happen there, which are associated with phase transitions in the Ising model, which is what is described here, and which tells you that describe to you the appearance of magnetization and the behavior of the magnetization as you change the temperature of the system. So that type of the calculations associated with this are associated with something which is called coarse graining, which is associated with making starting with the system, like for example the spins that you have there, starting with the system with spins up and spin down, and then use try and take that large, meaning small, very small scale description of the system, and substitute it for something which is of the same size of where you actually took averages, and then construct something smaller, but at the same time expand the constants in the system. The constants meaning the forces, the parameters that control the forces, and so on and so forth. In this case, what you do get is a system, like for example, if you were to go here, if you were to go to this model here, and you were to take the majority rule in each of these groups, then what you actually end up after you do that process called coarse graining, after first reducing the number of what you have and then expanding in the scale, what you do have is that the system readjusts itself, and it readjusts itself into a form of the old system, but where the physical parameters of the system actually have changed. In condensed matter physics, what you do is you introduce the so-called partition function. The partition function is some fancy functional integral And then this business of in this calculations, in this type of systems, many particle systems, you do have a problem, which is that there are infinities that appear in the calculations, and therefore they lose meaning. There is a way of resolving that, which is done through a trick, which is called renormalization, which consists precisely of rescaling, redefinition, and rescaling that I just mentioned in the previous transparency. And that introduces this equation that I hope you're seeing my pointer. This introduces this constraint, this differential equation constraint on the partition function. And that implies, that has a number of properties which percolate into the properties of the endpoint Green's functions, which is what you use to describe the correlations in the system and how the system actually does its physics. And those equations are written down here. I don't expect you to understand what exactly these equations mean, but what they mean is that what you just said earlier, that you need to change the parameters of the theory, for example, models, coupling constants, or magnetizations per domain, and so on. You change those according to a particular function, which involves all the fluctuations that are appearing in the system, fluctuations that can be thermal, if those are the ones which are operating, or the fluctuations which can be quantum, or fluctuations which can be due to the feeding of the system with external material. You can solve this partial differential equation for the probability distribution function, and you find out that you get a solution which has the property that, for example, for the 2-point correlation function, it has the property that when you go to limits of large systems, the functions behave, this function here behaves like a power of the argument. And this is so you get power loss for the Green's functions and power loss for the probability distribution functions. Power loss, of course, are indicators of the fact that a system is scale invariant. For example, imagine this is an arbitrary mathematical function, which is obeys a scale invariance, where if you take the function of its argument x, you require that the same function with the argument x expanded, scaled, is if you divide it by a, some scale associated with the function itself, this has to be equal to the original function. You can solve this mathematically, it's totally trivial, and you find out that the form of the function f of x is that of a power law. And this is what this is telling you is that this is scale invariant, and therefore it embodies the notion that the full system is involved in whatever dynamics you're talking about. So systems that, this is a first takeout, systems that actually are a power law invariant or display power law behavior imply scale invariance. That means that the system is somehow described in terms of a dynamics which is shared by all the components of the system. You can actually take that equation that you have there and study what are, put back this solution that C is x to the sigma, or the power law where sigma is some number, and then you find out that you have to solve this functional equation with these conditions, and that constrains the value of 1 over a to be something like 1 divided by lambda to the sigma, or lambda to the sigma is a, and there is an arbitrary unit here, which is the same thing as putting the roots of the unity, and therefore what you do get here is that lambda to the sigma is equal to 2 pi I n is a natural number between 0 and 1 times a. And then you find out that the exponent of the power law contains an imaginary part, which is written down here, which is an integer. So that is to say that the imaginary part of the exponent is discrete. This has important consequences because in condensed matter physics, when you have a system that is out of equilibrium, the correlations, like for example, correlations between density fluctuations of some kind averaged over the system, actually have a complex part, and the complex part, when you take the real part of this correlations are, these average correlations have to be real. They develop a form, they go into exactly what you have here, which is cos, which contains a power law here of the distances, and then times a cosine of a log of the distances also. This is called log periodic behavior, and you can actually see that there are regions in the system which are favored for things to for phenomena to occur. This is something which you can actually apply to the large scale structures of the universe. I'm not going to waste time with the calculations, but what you do show, you can show is the longitudinal size in centimeters, for example, for the molecular clouds, for scales between molecular clouds and galaxies or clusters of super galaxies to all the way to the COVID, the cosmic microwave background radiation. They actually correlate pretty well, and you are able to predict the existence of scales in the universe, which not only describe galaxies or clusters of galaxies, but also describe molecular clouds, etc. And that is a consequence of the non-equilibrium and the expansion of the universe in a non-equilibrium context. Power laws, of course, are encountered in many other contexts. For example, in biology, Jeffrey West and company have shown that all the allometric exponents that you find for mammalian living beings or for plants, etc., follow a particular power laws which they can actually describe. You can describe in absolute with extraordinary precision. There are many other types of power laws, and excuse me, there are many other phenomena which follow power laws and described by power laws. A power law which is not well understood, but it's related to some of the phenomena that we've been discussing this morning afternoon here with networks, is associated with metabolism. And you can also have log periodic behavior that is shown, that appears in, for example, in earthquakes. This is the log periodic behavior associated with the Loma Prieta earthquakes. And if you plot the cumulative Benioff strain release as a function of time, that is described by a power law, and each time there is a change in the argument of the law, or the argument of in the argument of the law, there is a release, and there is a good, for example, earthquake in the area, unfortunately. And that, as I said, there are many examples, and with those examples, one can begin to, using techniques from condensed matter physics, one can begin to think that perhaps one can establish some relationship between, or that there is some common theme between what is going on in the universe at scales where the gravitational force is dominant, where you get this power law behavior with the hierarchies, and what goes on in life across all domains of life that we see. So that the presence of these power laws bring with them, therefore, the possibility that we could find some type of unification in our understanding of this kind of phenomena, of large-scale phenomena, and the appearance of hierarchies through the applications of condensed matter physics through the renormalization group. And it's of course another way of reading what I had in the previous transparency is by other types of hierarchical forms that people have found. In the expansion of the universe, however, what one is doing is coarse graining dynamically, and dynamical cross graining is something that happens when you study, for example, when you begin to study, for example, chemical reactions which have many multiple sub-reactions or multiple components which have different scales, operate at different scales, or systems which are simply chemical systems out of equilibrium. An example which we started working on in the late 1990s. So at that time, many of you were not born or were about to be born. No, many of you probably were born at that time, this 95, 96. Are systems which are reaction diffusion systems with the stochastic term. When you do those, when you study those systems, you begin to discover that there is a renormalization group equation associated with, because of this, these noise terms, these fluctuation terms added to, for example, to some chemical species. It affects the feeding, and since this is a noise term, it's a fluctuation, and those fluctuations show up in changes of the parameters like the diffusion constants or the reaction parameters, the reaction rate parameters, etc., with scale or with the properties of the noise. What you find is that these systems can show a huge variety of systems like this. Can show a huge variety of behaviors, and let me see if I can. A huge variety of behaviors which depend on the initial conditions, and if you do a study taking into consideration the renormalization group of these systems, but for a certain set of reaction constants and diffusion constants, you get behaviors like that. It doesn't let me want to repeat the same trick over and over. If you change the parameters, you find further, you find that, and if you change the parameters even to other different values, you see things, you see regimes where the system generates structures from very simple components, generates structures which actually self-reproduce, die, etc., and you can actually show that they adapt to noise. So that can be used as a way of trying to see if one can apply this type of thinking, and one can find experiments to actually try and study first model, like for example, you can see in a work recently published by Alberto Pérez-Mercader and myself in Physics of Life Reviews, where you can actually show that this kind of thinking actually allows you to unify the properties or for properties of living systems. That is to say that the living system handles information, is capable of metabolizing, is capable of self-reproducing, and is capable of evolving by adaptive or non-adaptive strategies. You can actually unify them into a set of a small set of equations that, when you put them into the computer, they actually generate structures like this.
Juan, this is your requested 10-minute warning that you would ask me about.
Thank you. I appreciate that. I'm trying to thank you, Zach. I appreciate it a lot. So in these systems, the structures that you saw earlier growing, they begin. You can actually see how they grow. Here you have the size is represented by this curve. The information is represented by the blue curve, and this is actually a very good reproduction of the way the life cycle works in general in biology. And what you do see is that it mimics this. Now, what is the practical use of this? Well, this is an important point, which is that in order for the solutions to this equation to behave in this way, you have to have a very homogeneous interface between those. So, and then you can ask, well, what can we do in terms of phase transitions, or in terms of producing some sort of molecules which would have the ability to self-assemble and generate this something like this spontaneously under the control of the chemistry. So there is a type of polymerization which is called RAF polymerization, which can make, for example, polymers, including amphiphiles, with a very uniform length. So we began to, inspired by the solutions to those equations, then we began to look at RAF polymerization applied to some to the synthesis of amphiphiles, and we found out that if you take an amphiphile, if you start in a reaction vessel, you start with something which is hydrophilic, and it has a particular molecule here to continue the polymerization, and it's in a solution that contains monomers. And then there is I hope that this works. So the polymerization begins to make amphiphiles. This part is hydrophilic, this part is hydrophobic, and then they will actually organize themselves in such a way that they will self-assemble into what you might call this, into structures which, depending on the length of this tail, will be spheres like micelles, or the micelles will evolve if the chemistry keeps on going, acting on the polymers. The micelles will go into what we call worms, which are actually cylindrical micelles, and then eventually they will go into vesicles. And you can actually do that in the laboratory fairly easily. And you start with the solution, which is fully transparent. It contains the chemicals to actually carry out this pizza reaction. And eventually, with time, with 8 hours or so, you begin that the system begins to become cloudy, which means that it's forming this type of vesicles. And what you see, what you end up getting is what you see here. And that is, this is actually microscope image. The system which started like a homogeneous system now is not homogeneous, it's far from homogeneous, and it's generated, this is an emergent property, it's generated vesicular structures, and these vesicular structures, please keep your eye on this guy, but there are many who will do what this guy is doing. And these vesicular structures will continue. You see that they are reproducing themselves. You saw that this guy, the one we were looking at, collapsed itself and then began to grow again. And so on. We call this a type of assembled self under the control of chemistry, evolving under the control of chemistry systems. We call them phoenix for obvious reasons. And you can, if you look at them individually, you can see that they do this. This is a transparency that I added while the last speaker was talking, in order to just to show that the systems, simple as they are, they actually have the property that you can make different species, make them compete using Gauss's competition exclusion principle, and it works really beautifully as if it was real life. So it's the universe, and I'm getting ready to finish, is the universe in its expansion doing something like that with the chemistry that we have. I don't know. I subscribe, of course, to Vernadsky's ideas about why life exists and so on, but this is no proof of Vernadsky's ideas. But what is the proof is that a system which is coarse graining by itself, that is the chemistry, is making the system grow. The system, if it is a system which has the potential to exhibit emergence, then it will exhibit emergence in the form of systems such as what you showed. But what about the universe, the arrow of time working all the time? Can it do something like what the New York Times woke us up this morning with, like the pillars of creation, saying first with the visible and then the infrared, and can we say something about that? Well, I think the next speaker will be able to say a lot about how this works, and he has some really extraordinary ideas in this area, which I am sure will illustrate a lot of how these systems work. If you need anything from me, you can contact me here. Thank you very much for your attention. And I see that I've been talking for 29 minutes and 25 seconds, which is a record for me. Thank you so much.
Admirable
you very
time
much.
discipline.
I couldn't hear you, but I'm sure you were funny.
Are there any questions?
I might save mine for the question and answer session, actually, if that's okay for Juan.
Yeah, that's totally fine. And whatever you, is that Saidul?
That's right. Yes, that's right.
Hello,
Juan.
Saidul. Yeah,
Yeah.
whatever the organizers want, that's what I subscribe to.
You're one of the organizers. So I have a question too, but I can wait if you want to move on, and we can have a discussion at the end. So
I have no problem. What I don't want is to take a step over Eric's time.
okay, well, you're chairing now, so it's over to you.
To me?
I thought you were going to chair the last one. It's up to you.
Oh, yes. Okay. I tell you. So the next speaker is Professor Eric Chaisson from the Harvard Center for Astrophysics. He's a few years ago he wrote a fantastic book, which I'm sure he will talk about that, and where he presented some theories that he elaborated about the evolution of the universe and the formation of structure and life and more. And this is something which I believe is of particular interest to this community. And I'm very happy that he's going to present his work to us. Eric, anytime you want.
All right, I'm going to try to share my screen now. We'll see if this works. Whoops. Can people see that?
I can.
Is it okay? Can you hear me okay? And can you see the screen?
Perfect.
All right. All right, well, thank you, Juan. I hope you're feeling better today, Juan. And thank you all for sticking around this long. We've all been in this situation where with a last speaker in a longish meeting. So I'm going to be both brief and light in trying to propose or share with you one issue, and that is the possibility that there is a complexity metric, or at least a proxy for a metric that pertains to not only living systems, but all systems across natural science, and maybe even useful in categorizing and describing quantitatively systems that go well beyond natural science. Let me see. So I'll begin with an overview. And that overview always for me is the arrow of time. And I'm talking about all time now. I'm talking about time from the Big Bang to the current epoch on Earth. And we still don't know what that time is really. This morning's Astrophysical Journal brought a special edition, which reinforced the tension that exists between two different major ways of determining the age of the universe. But I'm not going to talk about that today, other than to note that whether the universe is as old as maybe 13.8 billion or 12.5 billion only, I'm prepared to move this arrow of time like an accordion back and forth. It's the sequence of events more than the absolute ages of events that have occurred over all of cosmic time. Provided that, of course, we maintain, hopefully, that all the objects we find in the universe have an age that's less than the universe. Otherwise, we've got a real problem. So I've identified atop the arrow of time here 3 different domains: physical, biological, and cultural, that I refer to as physical evolution, biological evolution, cultural evolution. I'm speaking broadly, I'm speaking writ large, in the sense that systems adjust, they change, they are selected by nature to either survive or not. And all of these 3 domains or phases of evolution come to me together into what I've called for years cosmic evolution. And I've offered the definition of cosmic evolution to you, for you there in the yellow oval. I'll read it to you. Cosmic evolution is a grand synthesis of developmental and generational changes in the assembly and composition of radiation, matter, and life throughout the entire history of the universe. A lot could be said about this arrow of time, but basically it's showing a Big Bang at the left and current Earth at the right. And it's a case where the arrow is trying to, in a cartoonish way, this is simply a graphic. We're not there to the quantitative barrage will occur in a few slides. It's simply a case of trying to capture the notion that the universe has moved from really inorganic to organic, from simplicity to complexity, from chaos to order in the old-fashioned Greek sense. This arrow is actually part of a much larger story I tell in class at different levels. This is the opening slide of a massive multimedia website that some of you may want to dip into. All of what I'm showing on the screen here now is hot in URL sense. And it's primarily pitched when you open up such a screen, and you could find it easily on Google by simply Googling my name, cosmic evolution, it pops right up, usually as the top element. It's principally meant for science for the non-scientists, which I spend a great deal of time addressing at Harvard, because I think in addition to training scientists, we really in the world today, if we are to, let us say, save democracies, we've got to spend a little bit more time as scientists devoting our efforts toward those who are not scientists, so that when they go into the voting booth in a technological democracy, they will at least be able to take with them some evidence-based decision-making, evidence-based policymaking. But in addition to the introductory nature of this website, which goes deeper and deeper over and over across that arrow of time, there is a parallel track that may be more of greater interest to many of the people at the meeting or your students, that does address this whole topic of cosmic evolution, systems change from Big Bang to humankind, at a level that may be useful to upper level undergrads or even introductory grad students. Now, the gut feeling we have, and it really is only a gut feeling, is that over the course of this same interval of time, plotted horizontally here, logarithmically now, that the system complexity has increased over the course of time. I'm plotting, therefore, vertically system complexity. And I'm going to define for you, I'm going to have the nerve to define for you complexity as I see it. Not that the complexity science community, as I know them, has come to a consensus as to what complexity is. So for the time being, I'll offer you my definition as complexity is a state of intricacy, complication, variety, or involvement, as in the interconnected parts, network parts of a system's structure and function. Again, I'm talking about system complexity, and that's what I'm heuristically and a gut feeling plotting on the left-hand side upwards. I'm not talking about the complexity of the universe per se, because I want to hold on to the second law of thermodynamics as the most cherished law in all of physics, the last one that I hope will ever fail after all the other ones have failed. And that second law of thermodynamics suggests that the universe in general, on average, in bulk, totally, is growing increasingly disordered, less complex, moving from complexity to simplicity. But system complexity, which is what I'm interested here today, as systems like islands of order in a sea of great chaos, is in fact obeying second law of thermodynamics in conjunction with the surrounding environment. And when I analyze whether they be galaxies, stars, planets, life, society, or the things we build, such as machines, over the course of time, we have this as is shown in these variety of shapes here, moving up and down from left to right. The gut feeling, or at least I do in my gut, intuitively, that there's been an increase in complexity within those systems. Now, you may want to call system complexity something different, as I've plotted, as I've written on the left: order, information, neg entropy, organization, inhomogeneity. Here's a better idea of what I mean about the three kinds of systems that interest me most, as part of what I think is one of the most interesting photos ever taken. It's at least a candidate for the coolest selfie ever made. And I had something to do with helping to create this. The astronauts were going up in the 80s to try to fix Hubble. And I was charged with choosing the first images that Hubble would look at. And so the astronaut, the spacecraft commander at the time, asked me, gee, is there any way, because they would still be on orbit having fixed Hubble, that they could see what Hubble was seeing? So we literally, believe it or not, arranged to send a fax of the first image we received at mission control on the ground up to the shuttle so the astronauts could see it. But in return, I asked the astronauts to get me this photo, or get me something like this photo, a photo that would dramatically show the three kinds of systems I'm interested in: physical systems, biological systems, and cultural systems. The physical system in this photo, of course, is the star, the sun in the background, along with the Earth. The biological system is Kathy in her EVA spacesuit. And the cultural system is at lower right, the space shuttle that brought her there. She's joking me around a little bit in arranging this photo by looking at her little worksheet that's strapped to her left arm, thinking that I would imagine it as her kind of lunch menu. But of course, all astronauts have on their left arm their work assignments, a little like a quarterback has on their arm, on their forearm, the various play assignments. I often wondered whether the astronauts got the idea from quarterbacks or quarterbacks got the idea from astronauts. I'm not sure. But in this photo, among these three systems, the one commonality that's of interest to me is that there's energy flowing through each of these systems. If the sun did not continue flowing energy through it in the form of luminosity, it would collapse. If Kathy did not eat 2,800 kilocalories per day, that is about 120, 130 watts per day, she would die. And if the space shuttle did not have a sufficient amount of energy flowing through it, it would not have flown. Energy seems to me to be a strong commonality among the various other things that I see in this photograph. So how do I analyze what I see in this photograph, namely those three kinds of systems? Well, I can ask you to consider thermodynamically a box. At least I'm not asking you to consider a spherical cow. This is just a box. And it's a box shown here embedded in an environment. And this box is open. It's open to the environment. If the box were not open to the environment, again, each of these systems shown in the photograph underlying here would die, would no longer exist. But the box is, as imagined here, open to allow energy and resources to flow in, as well as heat and products to flow out. In each case of the systems, these physical systems, biological systems, cultural systems shown in this photograph, among hundreds of others that I've analyzed, I can look quantitatively in greater detail at the entropy changes within the system and within the environment. And in every single case I've analyzed to date, over 20, 30 years, I find that indeed the entropy of the surrounding environment increases more than does the entropy decreases within the system per se. Such that if you consider this box in its greater environment, the system plus the environment, and add to the, you always have, in accord with the second law, we want to obey that, an increase in entropy overall, despite the fact that as long as the energy keeps flowing to the system, and there's a flow of energy through the system to create structure within the system and function as to not only what it is, but how it operates, then we can temporarily, for a period of time, lower the entropy within the box. 70 years on average for us in the West, 1 billion years for a star. Space shuttle lasted a few decades. Here's one way to graph it. Energy, E, increases over the course of time. And I show here just graphically, not showing any numbers yet, the increase in energy, the increase in entropy S in the environment, always exceeding at any one point over the history of time, the degree to which the entropy S for the system decreases. So I'm considering now these various systems, 3 kinds of systems: physical, biological, and cultural systems. I want to lay on you, because of the nature of the conference here, one aspect of the conference that puzzles me a little bit, and that is life itself. I've attended as a physicist many meetings over the course of time that have a biological nature to them, and hardly anybody ever attempts to define life. Or when they do, there's no agreement in the room. I've collected now in my career more than 120 different definitions of life. And so I don't think there's any obvious consensus among biologists, except for the quip that one often hears, that I know life when I see it. But of course, we all know that that's at least one Supreme Court justice's definition of pornography. My definition is shown here. I'll read it to you. Life is an open, coherent space-time structure maintained far from thermodynamic equilibrium by a flow of energy through it, dash. A carbon-based system operating in a water-based medium with higher forms of metabolizing oxygen. Wow, that's a mouthful. But at least I have a definition that I've thought through, that I'm willing to defend, but I'm willing to also revise and edit. Indeed, this definition has been revised numerous times, mostly among my students who attack me on all aspects of this definition, especially at the last line where I talk about higher forms metabolizing oxygen. But I'm not here to defend this particular definition now, other than to suggest that the common denominator in this definition, open, coherent, space-time structure maintained far from thermodynamic equilibrium, a flow of energy through it, pertains not just to life. It pertains to physical systems. It pertains to cultural systems. For example, I could offer you a definition of a star. It would say a star is an open, coherent space-time structure maintained far from LTE by a flow of energy through it, dash, a glowing ball of gas bound by gravity and powered by nuclear fusion. Or I could define a society. Society is an open, coherent, space-time structure maintained far from LTE by a flow of energy through it, a group of people living together in a common community. All of these systems, galaxies, stars, planets, life, society, machines, have flows of energy through them over the course of their existence. So here's the way I look at it. Here's the way I approach it. Here's the way I try to begin quantifying, because I'm an experimental physicist by training, an observational astrophysicist by avocation, an empirical materialist by philosophical bent. I'm looking for numbers. I'm looking for quantification for open, ordered, non-equilibrated systems. I'm not going to hang my hat on entropy, and I'm not going to hang my hat on information. I've tried to work these subjects for many years. I spent a good 2 years trying to deal with entropy, quantify it. understand negentropy and all of its slippery aspects. And I came away thinking, well, how am I going to measure this stuff? Have you ever seen a negentropy meter, like a thermometer, which we call a thermometer? And similarly, although there are so many of my colleagues who wish to embrace information and information theory, I'm going to put it aside as well, because I spent another 3 years in the 80s and into the 90s trying to understand how I could, for all of these systems over the entire history of the universe, quantify them in a uniform, consistent manner using information theory. I've just struck out. I'm sorry. I'm not smart enough to do this. It's up to somebody else to do that. In the meantime, I'm going to embrace the one quantity that I know well, energy. I can understand energy. I can define it. I can measure it. I know its units. I have an intuitive feeling for it. And I'm going to try to run with it. See how many open ordered systems identified out my window I can analyze in the same consistent manner. But it's not just energy. It's not just total energy, nor is it just the rate of energy flowing through a system. Because I know darn well if I go into my backyard that the smallest living system, a microbe or an amoeba in the brook in my backyard, is more complex than any nebula I see in the sky. So it can't be just a case of energy alone. Rather, I embrace the notion thermodynamically of free energy rate density as potentially the best way to move toward a complexity metric, or at least a proxy that would pertain to all systems from Big Bang to humankind, and that I label V sub m. I use my cherished units, which you don't like, ergs per second per gram, which is what we use all the time in the trench. Or if you want to, as you begin to see the numbers as I have for your consideration here in ergs per second per gram, if you want to embrace SI, simply divide by 10 to the fourth to get watts per kilogram. Now, energy rate density, you see the definition I've offered for you there. Energy rate density is a measure of the amount of energy available to do work flowing to a system per unit time per unit mass. It's nothing new. Everybody uses this in science. It seems like everybody has the same idea, but they all call it something different. My astronomer colleagues at the observatory call it the light to mass ratio. Physicists call it the power density. Geologists call it the radiant flux. Biologists call it the specific metabolic rate. Engineers call it the horsepower to weight ratio. Economists, they call it the energy per capita. Well, I call it what it is, energy rate density, because I want to emphasize it's the flow of energy through a unit mass. So let's build a table. Let's look at some of these different systems. Just half a dozen, because I don't want this to get out of hand. I'm looking at the clock here. I'm going to look at generic system at the left. I'm going to look at the value of phi sub m. That's the energy rate density in my cherished units, CGS units, at the right. And I'm going to also indicate an age for these various systems. And I'm going to begin with something like the star we know and love the best, the sun. And so that's a light to mass ratio. I know the sun's luminosity very well. I know its mass very well. I can determine the energy rate density of the sun. It's 2. I can do the same thing for a galaxy, any galaxy, but I love the Milky Way galaxy where I work most of the time. And I find it's about 0.1. I can go up and begin to build this table further, considering not only planets, but plants. And I can go further to consider animals and society. Now, I've just taken these sample values for the time being before I build my finale slide here in a moment to show you how, as I've moved from the bottom of the slide, galaxies and stars, physical systems, through the mid part of the slide, biological systems, up into the top of the slide, cultural system, you'll note, of course, it's pretty obvious that the value of phi sub m, energy rate density, is increasing. It's increasing rather dramatically. And it means that in terms of energy flow per unit time per unit mass, that there's almost 1,000,000 times more energy flowing through my brain per unit mass than through the sun. There's hundreds of thousands of times more energy flowing through my body per unit mass than through virtually any star. But you begin to see how if we have this notion that over the course of time, as we study these systems that might to be more complex, this quantity does trend along the lines of movement towards very small values, 0.1 and hardly more than unity for physical systems. That's typical. To in the vicinity of hundreds to thousands for systems that are on the edge of life, to something that's a good deal larger for systems that are collectively operating in a networked way, whole perhaps indeed becoming greater than the sum of the parts. Let's plot it. What am I plotting here? I'm plotting logarithmically energy rate density, ergs per second per gram vertically. Very large interval there, almost 10 orders of magnitude for the vertical graph, vertical axis. But across the bottom, I'm showing the same interval of time that I showed for the hours of time to begin this talk, over on the order of 12 to 15 billion years. And I'm showing the values for the various systems that I chose that pertain to us in the universe along, let's say, an evolutionary track that brought us to be. And I'm plotting their ages, and you see more or less there's a curve that begins to resemble the gut feeling graph that I began with in the beginning, where I suggested to you we all have this feeling that over the course of time, exponentially, or maybe even faster than exponentially, complexity has arisen. Indeed, this is a logarithmic plot vertically, so that an exponential plot would be straight line on this graph. This is showing something steeper than straight line. This is showing and suggesting that energy rate density among these various systems would have increased even faster than exponential. Let's look at some of the details. You can really move into the shaded area under this solid graph and look into and examine quantitatively hundreds of different systems, as I've done in various papers over the course of the last 20 years or so. All with my left hand. This is work I do with my left hand. This is work that I do when I'm a lumper, a unifier, whereas most of the day job I have is to be a specialist like the rest of you. Working with my right hand to write articles that, well, frankly, very few people read. But you can see without me running out of time here that one can examine in greater detail the extent to which we know how the galaxy at the bottom has changed over the course of time, how plants in the middle through gymnosperms, angiosperms of the midsection of the curve, how hunter-gatherers have given rise in the early rise of society, now have machines toward the top of the curve. Everybody wants to know where this curve is going. The answer is I don't know where it's going. Evolution is unceasing, uncaring, and unpredictable. I don't know where it's going, other than to suggest that it looks like it's going up, and it looks like it's going up faster and faster. But the interesting thing about this plot is shown in the yellow oval, where I claim it to be an example of ascent of with modification, Big Bang to humankind, on the same page. I have 10 orders of magnitude in energy rate density, expressed in 20 orders of magnitude in spatial dimensions from galaxy clusters to atomic systems, and nearly 18 orders of magnitude in time. Here I can read for you specifically why I suggest, and I've put in italics, proposed, that this might be, am I qualifying it enough? A metric or proxy for complexity. Mature galaxies are more complex than the dwarf precursors. Old red giant stars Old red giant stars are more complex than younger normal stars. Planets are more complex than their host stars. Plants are more complex than nucleated cells. Animals more complex than plants. Mammals more complex than reptiles. Brains more complex than bodies. Societies more complex than individual humans. Machines more complex than anything else to date. All of this is quantifiably supported. I'll just leave you with a penultimate slide before my final slide to suggest for you that in recent years, where I've really begun to explore, as I'm now moving toward semi-retirement, but I'll never actually retire, aspects of this study and exploration of how energy rate density might in fact help us here on Earth. Instead of looking out as I always have for my career, I'm looking back now. I'm trying to give back. I'm trying to explore whether or not these ideas can be used to aid studies of climate change, of cities and nations, of global world economic systems, smart machines, smart in the sense that we like to interact with them smartly, but not claiming that any of this has anything to do with intelligence. And cancer research, in fact, the oncologists at Mass General Hospital and Harvard Medical School have often called me to give thermodynamic seminars. It might suggest how desperate they are to cure cancer, I suppose, but in many ways they see some value in the flow of energy through tumors that could be either stopped or, in my opinion, made more optimal. And so there's a wide variety of applications whereby I now have embarked upon a program of, don't laugh, cosmology lessons for human society. I'm trying to explore whether or not this potential metric, a proxy for complexity metric, can be utilized to better us in our fate here on Earth. The final slide offers some representative bibliography if those of you want to look into this a little bit more. The first paper at the top is one of my earlier ones on suggesting ways in which this can be used as a very useful unifying concept for astrobiology. The second one is a more recent paper exploring in the journal Entropy why I think entropy is not the way to do it. That was an interesting interaction with a series of referees over the course of time before that article got published, in which I championed the role of energy flow in the Entropy journal. The third one is in my attempt to again demonstrate how I'm a lumper now. I'm not a splitter. I'm mostly moving toward trying to unify the sciences and maybe beyond. The fourth indicator here suggesting how we can in fact go beyond to consider economics, to consider history. I often meet with historians at the faculty club who are so proud of the fact they go back to Babylonians and Sumerians, and I lean over and say, hey, I'm an astronomer, I go all the way back. And I think there are nonetheless cosmology lessons that economists and historians and others, engineers in particular, could utilize well beyond natural science per se. And the final entity is a paper that was published today in Europe where I'm exploring the energy budgets of evolving nations and their growing cities, trying to explore whether or not this free energy rate density concept can help us to ensure that nation states endure, because there's nothing assured about the survival of states, cities, and nations on this planet. Thank you very much for inviting me again. I've enjoyed this meeting very much.
Thank you, Eric, and for a very thought-provoking talk. There are a bunch of questions for you. But what I suppose, I would like to ask Zach and Jennifer is if we could move from here to the discussion panel, and then we can entertain the questions in the discussion panel in the interest of time and of ending at the hour. So with that, I would like to turn the control to Zach.
That sounds good. And if it's okay, if we have each of our speakers, if you're present and showing your video, just so that we can have you up here, that would be very helpful. And thank you very much, all of you, for closing out our first 2 days of formal talks on this. This is, exactly the topic that I think we kind of wanted to use as we transition to our discussion and synthesis for exactly how all of the things that we learned may relate to prebiotic chemistry. I think before we do anything, let's go back in to address some of the questions for Eric's talk that were presented in the chat. And perhaps I'll do Stuart Bartlett's question first because it's pretty generic. And then perhaps David, you could ask your question directly as part of the panel. Stuart was asking, if we choose relatively small volumes or boundaries within which to measure energy rate density, what values would we calculate for, say, an exotic event, like something that's not about let's say not a steady state process or a long duration process, but a very short event such as a black hole merger that creates, say, detectable gravitational waves? Is that outside the scope of your assessment or this use as a proxy?
Yeah, I don't know the answer to your question, of course, but I have considered that many of the events that I see that are of short-term duration, such as supernova explosion or black hole merger, these are not within the realm of something that moves toward greater complexity, as I see it. These are something such as a bombs, supernovae. They're phenomena that move toward greater disorder, more simplicity. So I like to suggest that they don't belong on my plot. My plot is an attempt to show how there's a rise of complexity in nature over the course of time. And so I've conveniently swept them aside, though in writings I've pointed out in greater detail why I've swept them aside. I just don't think they belong.
Right. And then Donald Burke asked the question, the progression you show for n=1 for Earth-specific components, how much wiggle room might there be in the x-axis for a non-Earth technological planet? For example, could technology have emerged elsewhere at 3 billion years or 6 billion years?
Sure. The curve I showed was pretty much our world line, the world line that went from Milky Way to Sun to Earth to us. Other alien beings, of which I'm guessing there are some there, or even if they're not alien in the intelligence sense, just planets with microbial nature, creepy crawly life elsewhere, would have similar world lines, but wouldn't have to parallel ours exactly at all. So, but in the lack of data and an empirical materialist, I don't know what to do with that. I mean, I sat for a dozen years with Sagan and Drake and Jill Charter and the rest on the NASA Science Working Group for SETI, and we examined all sorts of possibilities, but never came to any conclusion that there's any evidence whatsoever for evidence for life elsewhere. I also got inside as a former Air Force officer inside of Logic Blue Book to see whether or not there was anything there. And I can assure you there's nothing in there. Nothing in there. And so while theoretically there could be a whole family, hundreds, thousands, infinite number of different life forms that have emerged in other alien systems, I just don't know what to do with it.
Right.
No data.
I've got kind of a general question. This I think might tie in, and anyone else feel free to drop questions into the chat or to raise your hand. I'm just kind of helping to moderate this and trying to encourage our speakers to speak amongst each other. And I want to draw in both Ella and Juan into this question. Is there a role for, like, let's say for Ella in your assessments of dimensionality in phenomena and energy rate density, and Juan, does that tie in any way? You touched on renormalization and scale-free phenomena. Are either of these challenges to characterizing, complex systems, either in terms of degrees of freedom or in terms of long-term development of steady states or something like that? Does this have any? Does anything of what Eric had touched on in his talk have any relevance or bearing in terms of your respective disciplines?
I mean, Eric's talk was brilliant and eye-opening. As a human, I don't like machines being at the top, so I might argue that they should be more energy efficient, and maybe we could regain the top. But as technological creatures, the machines are also us and part of us. And so, yes, that's slightly an aside.
Agree.
I am interested in looking at this concept and the stuff I'm looking at. In terms of a measure of complexity, one of my planned next bits of work is to take the topological features I was talking about earlier and apply it to proteins across the evolution of proteins. Has, in some fundamental topological way, the active site of proteins changed over evolution? And I know there are some proteins that are very similar as you go across the Archaica, I think they're called. I am not a biologist. I'm going to go find some biologists to ask how to structure the actual question I need to ask, but I'm going to look at it from that side. But this energy density approach does seem very useful as well. And I imagine that whatever we do come up with as a measure of complexity, it's probably going to be different things, and they're probably going to turn out to be, in 200 years time, people will be saying, oh, they're really the same thing, but they were talking about, she was talking about shape, he was talking about energy density, why didn't they see them obviously this other thing? So that's my fault.
Yeah.
If I may.
Yes.
And
then we'll come back to David after your comments, Juan.
Oh, there is, oh, David, I didn't see you. Please go ahead. Go ahead. I can wait.
Oh,
David?
okay, thanks. Yeah, Eric, I was wondering, when I read your paper, and I thought I saw it again today, I wasn't sure what you meant by energy, how you calculate this. So like you said that a technologist, I think, was like 1 or 2 orders of magnitude more, had a higher energy rate flux density than like an agriculturalist or whatever. It seemed like maybe that the president of the United States would have a higher one than like a tennis player in high school or something. One seems to be expending more energy, but the other one is somehow the president is directing like forces through a battlefield or something, and that like you would somehow count that. But I was wondering if I'm getting that right and how you do the accounting.
Well, I'm trying to analyze, for example, in the case of hunter-gatherers, the extent to which they physically consumed food per day, plus any additional efforts they made to utilize energy. And then over the course of time, trying to understand how individuals, not society, not the whole government collectively, but individuals come to utilize more energy over the course of time, during the agricultural revolution, during the industrial revolution, during the times now when you and I, for example, have on our desk a variety of energy using equipment, energy providing, systems that require energy to be used for our personal benefit. So,
so you're including like plugging in my laptop as part of the energy that flows through me?
Yeah, I would include the extent to which you're using energy in your daily life. For example, I'm taking down a certain amount of 5,500 kilowatt hours per year through my solar panels on my roof. That's provided to me in a household of now 2 people. So there's a variety. I'm driving a car a certain amount of time. So that's for my, it's like a carbon footprint, but it's an energy footprint that each of us has individually. And a person like you and I, who are working in a high-tech area in the 21st century, have a significantly higher energy rate density than a mill worker in Asia, than somebody growing a rice field in Indonesia. The average value across the world is about 25 kilowatt per person, whereas we in the West, in America in particular, in Canada and Australia and in Dubai, all have about several times that, as much as 10 kilowatt per person.
So for the president of the United States, you might count Air Force One as part of the energy that flows through them, but not the fact that they can make tons of explosions happen on distant battlefields. Is that right?
No. Well, I think warfare is another case of transient high-scale energy usage, like a supernova or a bomb that's not useful in terms of creating additional complexity. And we're seeing that where I was near recently over there in Mideast. But I don't, I'd rather take Air Force One and aircraft, and I've examined all sorts of evolution of Air Force aircraft and civilian aircraft, showing over the course of time, the amount of energy fueling those aircraft does increase per unit mass, per unit time. The energy rate density is increasing as aircraft evolve. But I'm not sure the extent to which I need to incorporate the amount of energy that a president would use in utilizing his aircraft, unless, of course, I'm doing that just during the period of time when he's in the aircraft. I mean, I haven't done any.
Yeah, that is kind of my question: is where the boundaries get drawn.
Yeah.
And
Well, I think you're appealing to the next generation study that's going to have to be done by somebody who's younger.
I would actually almost want to turn the question back to you, David, and say this almost seems like a challenge of, say, category theory, where we deal with, say, something like some cohesive or coherent operating structure, like a society or a group of people, for which there is severe, heterogeneities within the group, and yet somehow it's acting like a coherent structure. There's some description for why, say, some group of people are going to behave according to one structure and one group is not. And it's it seems to me, hard to separate if they're operating as a coherent structure and there's one individual designated as being in charge of more resources than others, and yet they are a coherent structure. That might lend some support to, say, averaging over that coherent structure versus a larger, say, species-wide perspective or a society-wide perspective.
Yeah.
I'm just I don't know if that's
Wait.
valid or not.
Hey, you guys, this is Lauren. I have a problem with all of this, which is, I think, if you look at human society, which you're making a big deal of, this is like a millisecond in the history of the Earth and will probably end in another millisecond and should not be taken to represent very much. I mean, I don't see why you're making such a big deal about, human society, which, let's say it's gone in 1 million years, probably is, right? Then if it's gone, then what happens to your graph? It like totally turns around, doesn't it?
Is that different for the solar system, which will only be, 1 billion times longer or 1 trillion times longer than that? Like, every number is relatively small compared to the size of larger numbers.
Yeah, but his measure of complexity is totally based, or this flux is based on human society. And when that goes away, which it will probably, which obviously it's going to do, then everything turns around, right? Your graph heads down in the opposite direction. Your graph turns around and goes in the opposite direction. So I don't see the validity of this at all.
Well, in fact, if you look at species, biological species that have gone extinct, you see that, in fact, the energy rate density dives. If you take a look at cities and nations that are now failing, I could name some of them, from Haiti to Detroit, you see their energy rate density is falling.
But you're focusing on such a tiny, tiny part of biological history of the Earth. For 2 billion years, there was only microbes, right? So you had a constant, what was going on then, right? You're only talking about a very specific part of eukaryotic biology. You should not think that this represents life in general. It does not.
Well, actually, Lauren, that it kind of gets to what we were just talking about with the problem of subdivision and heterogeneity within a group of anything. So, for example, I kind of get what you're saying. I think you're saying that this, perhaps the way that the plots were depicted and shown here, it's showing something like a teleological thing, like there's actually a trend or a pattern, and that somehow it's predisposed to continue that way. But when you pay attention to differences within, say, whatever classification or within whatever grouping you're assessing, those fluctuations can go up and down at any given moment, as opposed to a historical description of class that just
I would add one more thing to that, which is that people always overestimate their significance, which seems to be what is happening here, right? You're saying that this whole trend you're talking about is really all about humans, and I don't think that's I think that should be a danger.
I'm not sure how you can say it's all about humans. I mean, my story extends from Big Bang to Humankind. Humans are just the most recent addition to my story. I agree with you that we are the ones telling the story.
Can I make a comment here? I think there's a misunderstanding. The graph which was shown for the energy consumption includes all life, not just humans. Only that the rest of the life didn't increase with time, so it doesn't contribute substantially. So it's not about humans, because humans are more important, just the energy consumption of the whole ecosphere of Earth. There's nothing to do with humans believing they're more important or not.
All right. It is, because humans are just such a small part of biology and are probably not long for this world. So that whole upward trend is going to inevitably turn around and go back down.
Lauren, if it
misleading.
Suppose if machines do succeed us, I could easily see potentially the next phase of systems complexity. It might be machines, it might be a hybrid with humans, continuing on rising up, even if our society today crashes and burns.
But even then, this is the null hypothesis wouldn't be that, or there's nothing to say that the number couldn't go down.
Absolutely.
That it's if humans did die out in the next microsecond of evolutionary time, then if someone was around to plot it, it would certainly go down if someone was actually remarking upon it. So there's nothing in your talk is implying that there's an inevitable upward trend that's consistent over time or time.
Right, but that's the most recent efforts that I've been making to see whether or not there could be ways to gain insight through energy rate density analysis to extend the endurance of human society. It just may well be that we will endure for a good long period of time. I'd like to think that will be the case. And I'd like to contribute to that positively if I can, rather than be a doomsdayer.
And I think perhaps that's the nature of the discrepancy or disagreement between you and Lauren, is just that that whether or not it continues upward is really unknown at this point.
Absolutely.
Yeah.
I think there's a general disagreement among scientists about the view what complexity means. So traditionally we have seen or believed that the evolution of our ecosphere on the Earth to become more complex, to be something implicitly also something good or interesting. Now there are a substantial number of people who are saying, oh, that is very human-centered. A world where only bacteria is as valuable as a world where there are also complex animals. And I think the discussion here is a little bit along these lines of views. So normally it has been attributed that more complex life is more interesting, and other people say no, bacteria, world only with bacteria is enough. There's no need for nothing good about more complex life to evolve. I think it's along a similar discussion.
Lynn Margulis used to say that human life was the most interesting form of life, but that ultimately the microbes would likely inherit the earth.
Eric, can I ask another question about your talk? At first you were talking about entropy, and somehow entropy mathematically is easier for me to understand than energy. And then
can you measure it? And can you measure it? Can you measure it?
That's the issue that moved you to energy.
Yes. I've never seen an entropy meter. I can calculate it, sure. You and I could sit down and calculate theoretically any degree of entropy. And it's useful as a bookkeeping tool to make certain, in my mind, that I'm always in accord with the second law. I'm always worried that I'm going to encounter a system that does not obey the second law, which many people have previously thought was the case with life. And of course, we know life is in complete accord.
But isn't energy also difficult? Like the fact that there's kind of different forms of energy, chemical energy, motion, etc. Is it like what do all the different forms of energy have in common? What is energy? Like entropy might be some kind of just calculation of the number of states something can take on. But what is energy? I feel so sad that I don't know yet what that is.
And energy is the ability to do work or to cause change.
The work itself is, to me, they have the same units, and there's no, like, what is work then? What is ability?
But I can measure that in units that we've all agreed upon. in a consistent
Right,
way.
but the units of mechanical energy and chemical energy are the same units, but are they the same?
When I
Okay.
eat food, I'm energizing chemically. When I plug in my laptop, I'm getting information electronically.
So it's just a number. It's a real number, and that's that's all it is, and it's the capacity for movement through space, basically. I don't know.
I think it is just a number, but it's a number that I feel I can quantify consistently for all systems, and it's a number that I can measure with an instrument.
Yeah.
I've never encountered an entropy meter. Have you?
No, I'm not saying I like that one either. I don't really know what to
Okay.
Well,
I'm gonna jump in here and say,
entropy is a measurable quantity in physics.
Yes.
It's observable, but it's of course not an entropy meter, but you have to integrate it up specific heat. And when you integrate up specific heat, you get the free energy and the entropy. So entropy can be measured, but of course, otherwise physics doesn't work with not measurable quantities, but it's not as direct. So energy is much more direct, but energy is very physical.
Well said.
Yeah.
I'm going to jump in and say Eric, I first came across your writings some number of years ago, and one of the reasons I found myself keep trying to come back, get away from it, and kept coming back is that it's inescapable that any phenomena such as life has a need and absolute requirement to exist at a gradient of energy. It's a question of, how large that gradient is, or over what span of time it becomes more distributed or diffuse, or however you want to measure it. But it's
an optimal range above which and below which life will not continue.
Right. I'm gonna shift the conversation just slightly back to we had some questions for Ella, and I think this is an opportunity also to say that we're kind of looking at this at an organismal level, kind of by default, or a societal level, but perhaps some of these questions would apply at a polymeric level or a pre-cellular unit level. But Donald's question specifically, Ella, are you there? Able to take questions?
I'm here.
Yeah, did you see the questions in the chat?
Yeah. Do you want to read them, or I can reply to them?
Please feel free, go right ahead.
Okay, so the first question, you represent chemical species by projecting them onto icosahedra with faces acting as pixels. What kind of molecular characteristics limit what can be encoded this way? Can you do large proteins or ribosomes? Well, I skipped over that in the talk, obviously. So the method I'm using at the moment, I lose quite a lot of information. So I was taking the innermost atom of the active site, which the origin was, the active site was in the mid, sorry, the origin was in the middle of the active site. Take the innermost atom, its atomic mass, the outermost atom, its atomic mass, and the sum of all of the ones along that line that hit that face. So we lose a lot of information doing that. And the second question, can you then reverse the process and ambiguously reconstruct the original molecule from the pixel pattern? So the way I do it at the moment, not quite. Reversing it is obviously something I want to do. You'd have to use maybe a machine learning system, or maybe you just get that information and you have an algorithm to sort of guess what it might be and then optimize. However, I do know how to fix this problem, because if you saw the molecule rotating and you saw the pixels and how the things move, if instead of encoding it as individual pictures of the rotation, I encoded it as how each atom, so now the atoms have a label, each atom moves over that pixel space during a, say, 360-degree rotation for all of the atoms in the protein, then that would actually encode all of the information. Then you need to use a different neural network. Now you've got sequence data, transformers, everyone is very excited about. I haven't really poked at them yet, but they look like a good option. So this is, I'm a bit bemused at the idea of a neural network having enough sort of memory to deal with a big sequence like that, but it is possible. So that's the next step on that one, and that would aid at the reconstruction. And as for how many things you can do, it depends how many pixels you have as well. You can make it more and more fine-grained. I only went to an icososphere of size 4. So as I said, the things I was showing you were very coarse-grained and lots of information was lost, but we can increase that. So I hope that answers all the questions.
Yes, nice. Could I add one more layer onto that, which is what you're suggesting is that as you look at effectively the time dependent pattern, time dependence of the pattern, then you're sort of adding a third dimension to it. It's a two-dimensional plot when you just have the pixels laid out in a grid, but then the time dependence of that as you rotate the molecule then adds a third dimensionality to it, which really increases the richness of what's being plotted there. Yeah, converting that back into an actual molecule would be an interesting challenge.
And it's a different thing if you take the snapshots and shuffle them, which was some of the results I showed you. So then all the neural network's getting is a picture of the frozen molecule from a different angle. If you put it in a sequence like I did in the slides, then it is, as you said, it's getting the time dependent information, which is more rich. I think it is possible to go back the other way. It's not a lossless transition, but like I mean, admittedly, there was a little bit like I like neural networks. I throw neural network at the problem here, and then I used to do quantum in molecular dynamics, so I just optimized what I get out at the end and hope for the best. But I think that would actually work, to be honest. So yeah.
Thanks.
And just to bring this background really quickly, Juan, you had a question in by I think it was by Saidul, who was saying that your talk had more of an element of a top-down approach. What are the merits, do you think, of more of a bottom-up approach and the strengths of either?
Well, I replied to him through the internet. Through the chat. He's already gone. He just left the meeting. But that was a very interesting and very perceptive question he asked. Most people would think, or many people would think, that what I am doing, which is putting together from small molecules systems that behave like a generalized living system. I don't need to define life and just characterize it. And there are 4 properties that characterize it, period. So most people would say that what we do by taking small molecules, putting them together and so on, and letting them control themselves and so on, is bottom-up approach. I disagree with that. And the reason why I disagree with that is because I know what bottom-down means and top-down means in computer science, which is where the terminology was, where the terminology originated. David Brooks introduced that terminology many years ago in the 60s. In fact, Nicholas Wirth is somebody in computer science, is the guy who actually started discussing this when he was designing the IBM 360. Top down is the same thing as inside out. In other words, you look at the system without, in general, from the outside, without thinking how it is made, how the sausage is put together, as they say. You look at the system with its properties in toto, incomplete, and then you go outside in. That is to say, from those properties which characterize the system, you go and try and determine what are the properties that need to be, or what needs to be happening inside in order so that the system behaves as a system that way. So top down and outside in is the same thing, and bottom up is the same thing as inside out. And I think the confusion comes from persons who, before I continue with that, this terminology is used correctly in astrophysics. Astrophysics, when people say top down, they mean galaxies first, or clusters of galaxies first, and so on, to stars. And bottom up is the other way around. And the solution to that question I don't think we still have. But in a lot of the contexts of what they call synthetic, which is not synthetic biology, like the one that which is extraordinary in genetic engineering and so on. People, I think, for some reason, they think that by putting the genome together, which is actually copied, by the way, from an existing natural genome, by putting the genome together, they are actually starting at the simplest possible level. And that's why they say bottom up, which is not consistent with what is used in the other terminology, in the terminology of computer science and so on, which is the one I adhere because it's the one that I understand better. I mean, we start thinking about life by thinking about systems which are chemical, they're open systems, the chemical systems which are open, therefore they are out of equilibrium, and they execute these four functions. That's what we, meaning many people, including, for example, somebody mentioned Eigen, Paul Nurse, by the way, has a beautiful book that came out last year discussing these questions, and he also identifies life by these properties. So those can be easily, well, easily is of course a huge exaggeration, but you can think just as if you were building a computer program that you want to do something, some function, then you think of which subroutines must there be and which do loops and so on must there be in the system so that it does what you want it to do. So the subroutines are the parts that you need to put together if you want to build a chemical system that you want to identify like a living system, then it has to for sure execute those four properties and be based in chemistry. So you need to think about how to, one subroutine would be to make sure that the system is capable of handling information. Another subroutine, another part of the system is making sure that the system is capable of metabolizing, that is to say, get parts in the environment, simple parts with which it will build its own parts, and eventually the parts that will go to make it its descendants, and also, of course, do handle, manage energy and so on. Then the system will, with those two properties, should be able to have the machinery inside that makes it self-reproduce, not self-replicate, self-reproduce, and adapt. So those four components need to be connected in some way, which is where the tricks are. This is a view which was espoused by, I forgot his name, his first name, Miller, somebody who was studying living systems, and he came up in the 1970s with a very voluminous book on living systems. But this is the view he had of putting those systems together. He was not thinking like we are. We in particular, my group and myself and others, other people in other laboratories. What we are trying to actually do is make a system which actually is capable of doing those things those four things independently, and then they integrate easily or naturally, and it happens in the lab under the control of the chemistry, and it does happen in our case.
Okay, I think at this point we were a bit over time, and I am very aware that one of our co-organizers is very forward in time relative to our time zone here. But this is I'm very glad to see that the talk sparked some discussion and debate about what, how this is a very, very difficult problem as to how to characterize, and to borrow a term from David's talk, how to categorize and actually, codify formalisms for groups of objects. It's very easy to say we can see the relationships at one level and how they're affecting or being affected or co-affecting or co-interacting according to rules that might be formalized in many different ways. But the challenge really is, how, when the rubber meets the road, how do we measure these things? What things are measurable to begin with, and which of those metrics may or may be more or less significant? It's not at all clear, how we might do this, and so it's a topic that's worth debate, and it's a debate worth having. So with that, I think we'll try to close out this part of the discussion for today. Just as a reminder, we are meeting tomorrow. It's a session that will not be recorded. It's just intended basically to pick up this conversation where we left off with our panel members and with one of the PC3 leads, Lauren Williams, as a de facto honorary panel member for jumping in. and engaging so vigorously with our topic. We're hoping to pick up the spirit of this discussion tomorrow and to break out into smaller groups to try to tackle some of these things and to try to make some progress for integrating a number of the topics that were discussed today into our ongoing organization of our community. So with that, I really want to thank each of you for staying on past the stated time. I want to thank all of our participants who joined us for these meetings and the people who will be watching this afterward through the YouTube channel. We had a number of requests for people who weren't able to make it yesterday and today, so they will be picking it up later. And we want to thank you for your time and attention and for all of the wonderful talks. Thank you so much for joining us. And with that, we'll close out the session.
Okay.
Thanks, everybody. Thanks,
Thank
Zach.
you.
Thanks to the speakers, and see you
Thank you.
tomorrow.
Bye-bye.
Thank you, Jennifer. Thank you, everybody.
Thank you, everyone.